Before the first tick of time, before space had a single direction, there wasn't even emptiness. There was nowhere for nothing to exist. And yet, the universe erupted into being, carrying every galaxy, every atom, every thought you've ever had. So, what did it begin from? And when physicists say nothing, what are they really claiming? Nothing is not a place. It is a claim, and the claim is on trial. Tonight we follow the evidence to the edge where physics must invent its own language. The universe looks ancient, orderly, and strangely comprehensible, yet its first chapter reads like a contradiction written in light. We see galaxies fleeing in every direction, a faint microwave afterglow, and a chemical signature stamped into hydrogen and helium. These clues do not merely suggest a hot beginning, they form a forensic record that can be cross-examined. But when we rewind the cosmic film far enough, the mathematics stops describing events and starts describing its own limits. At that boundary, beginning becomes a technical word, and nothing becomes a word with several competing definitions. In this documentary, we will treat each definition with discipline, because a single careless phrase can smuggle in hidden assumptions. We will move from the familiar darkness of empty space to the quantum vacuum, where absence can still carry structure. We will ask what it means to speak of time when time itself may be emergent, not fundamental. And we'll confront the Planck frontier, where gravity and quantum theory collide, and intuition fails without apology. Some proposals round off the start of time like a smooth cap. Others replace a singular origin with a bounce, a transition, or a deeper phase. Inflation enters as a daring mechanism that turns microscopic uncertainty into cosmic architecture. Yet it raises new questions about what counts as an explanation. Along the way, we will separate what is measured from what is inferred, what is elegant from what is testable, and what is unknown from what is unknowable. This is not a story about a single moment. It is a story about the price of asking for first causes in a universe governed by equations. Because when physicists say nothing, they may mean an empty geometry, a lowest energy state, or the absence of classical spacetime altogether. Each meaning changes the stakes, and each demands a different kind of evidence. So we will listen for the universe's earliest whispers in the patterns of the cosmic microwave background, and in the statistics of primordial ripples. We will follow those ripples back toward the era where even the idea of before may be a category mistake, and we will do it without pretending that mystery is failure, because in cosmology, precision about ignorance is a form of progress. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Chapter by chapter, we'll test the Big Bang as evidence, cross into the Planck epoch, and interrogate the vacuum itself. Then we'll explore inflation and possible pre-Big Bang scenarios, watching for the subtle fingerprints they might leave behind. Begin with a harder darkness than outer space, because outer space is already something. It has distance, duration, and rules that let events happen. In the visual imagination, even a black star field has geometry, points separated by angles, light with a travel time and a quiet sense of over there. When people say nothing, they usually mean empty space with the lights off. Cosmology means a stricter nothing, with no space-time, no fields, and no clock. It is not merely absence of matter, but absence of the arena in which matter could be absent. That difference is the first trap in this story, because physics normally assumes a stage. Even quantum theory starts with time, equations, and a background to define change. We can write down a wave function, but we still need a parameter that tells us what later means. So the question sounds simple and becomes slippery as soon as we touch it. How did the universe begin from nothing, if nothing has no place to begin? If there is no before, then even the grammar of the question starts to wobble. We are not chasing a slogan, and we are not trying to win an argument. We are testing what modern cosmology can actually claim, and what it cannot. The mystery is not a gap to be filled with confidence, but a boundary to be mapped with care. The phrase universe from nothing is controversial because it mixes everyday language with technical definitions. It is also motivating because it points at the deepest gap in our models. In public speech, nothing is absolute. In physics, nothing often means a specific measurable baseline. Cosmology is the study of the universe as a whole, including its history and large-scale structure. It uses the same physical laws we test on Earth, then stretches them across billions of light years. Creation is a word with philosophical weight, and science handles it carefully, partly because science measures processes, not ultimate meanings. The Big Bang sits at the centre of this tension, because it is both successful and incomplete. It explains much of the early evolution, but it does not yet explain why there is anything. It is a narrative of change, not a final answer about existence. First, we need to say what the Big Bang is not. It is not an explosion of matter into pre-existing space, and it is not debris flying from a central point. The familiar fireball image misleads, because it smuggles in a surrounding emptiness. In the standard picture, space itself expands, carrying galaxies apart as distances grow. Every observer sees others receding, because expansion happens everywhere, not from a single centre. If you could ride a galaxy, you would not feel a wind, only the slow, relentless stretching of the cosmic scale. There is no known outside that the universe expands into, because outside would require a larger space. The model describes relationships within spacetime, not an edge pushing into emptiness. When we say the universe expands, we mean the metric changes, distances between moving points increase. This is where language fails us, because we picture blasts and borders. The mathematics instead tracks how the scale of space changes with time. On screen, a grid can swell smoothly. No privileged origin, no rim, only growing separation. The Big Bang model earned its place through evidence, not preference. 3 pillars anchor the idea of a hot, dense, early universe. Each pillar is a different kind of fossil, light, motion, and chemistry, preserved across cosmic time. The first pillar is galaxy redshift, measured across the sky and across time. Light from distant galaxies is stretched, showing that space has expanded during its journey. In spectra, familiar atomic lines slide toward longer wavelengths, like a musical note dropping as the instrument moves away. Edwin Hubble's early measurements were crude, but the pattern held and grew precise. His work built on earlier clues, including Vesto Slipher's redshift observations, which hinted that nebulae were racing outward. Expansion implies that the past was denser, hotter, and more compressed, because rewinding the scale factor squeezes everything together. The second pillar is the cosmic microwave background, a faint glow filling all directions. It is the cooled afterglow of a time when the universe became transparent. Today, it is microwave radiation at about 2.7 Kelvin, so cold that it hides in plain sight, detectable only with careful instruments. Before that moment, matter and radiation were coupled in a hot plasma. Photons scattered off free electrons so often that the universe was like a bright fog with no long sight lines. When electrons and nuclei formed neutral atoms, light finally travelled freely and still reaches us, an ancient message that has been in transit for nearly the age of the cosmos. The background is not just present, it is patterned with tiny temperature variations. Those ripples map early density differences that later grew into galaxies and clusters. Visually, the CMB looks like a mottled heat map, blue and red freckles that encode sound waves in the primordial plasma. The third pillar is primordial element abundances, especially hydrogen, helium, and traces of lithium. Big Bang nucleosynthesis predicts these ratios from conditions minutes after the beginning. In that brief window, the universe was hot enough for nuclear reactions, yet cooling fast enough to freeze the outcome. Those predictions match what we observe in ancient gas clouds and old stars. The agreement is not perfect, but it is strong enough to constrain the early universe. Even small discrepancies matter, because they can point to new particles, altered expansion rates, or missing astrophysical details. Together, these pillars tell a consistent story of a universe that was once hotter and denser. They do not tell us what happened at the first instant. Evidence gives us a trail, but the trail fades as we approach the earliest boundary. The model runs backward toward an extreme limit, and the equations begin to misbehave. Densities rise, temperatures diverge, and our description points toward a singularity. In the simplest extrapolation, the scale factor shrinks towards 0, and curvature grows without bound. A singularity is not a place we can visit, it is a sign of breakdown. General relativity predicts it when pushed beyond its domain, where quantum effects should matter. It is the theory's way of saying, the map ends here, because the assumptions used to draw it no longer hold. This is the central tension of the documentary, and it is not a minor technicality. The universe appears to have a beginning, yet our best physics breaks at the start. We can describe expansion, cooling, and structure formation, but the origin itself sits behind a veil. So what is t equals 0 if time itself is part of what begins? If there is no earlier moment, what does cause even mean? Causality is usually a chain inside time, and the first link challenges the very idea of a chain. Some answers treat the singularity as real, a boundary where history starts. Other answers treat it as a warning that we need a deeper theory. In either case, the word beginning becomes technical, less like a calendar date, more like a limit of description. Here we introduce the first key voice, Stephen Hawking, who asked whether the universe needs a beginning in time at all. His boundary proposals suggest a universe without a sharp edge, where the question of before becomes undefined. In the famous no boundary picture, time near the origin behaves more like a spatial direction, smoothly rounded, not abruptly cut. Hawking's work does not remove mystery, it relocates it into geometry and quantum gravity. It challenges the intuition that every event must have an earlier cause. On screen, the idea can be shown as a surface with no edge, finite yet unbounded, inviting the listener to reconsider what a start looks like. We also introduce Lawrence Krauss, who argues that physics can produce universes from nothing. His popular claim depends on defining nothing as a quantum vacuum with laws and energy structure. In that framing, nothing is not emptiness, but the lowest energy state permitted by quantum fields. Critics respond that a vacuum is not nothing, because it assumes fields, equations, and a framework. The debate is partly physics and partly language, and it shapes public understanding. It also exposes a deeper tension, whether laws are discovered features of reality or presupposed ingredients in our explanations. Between these poles sits a broader field called quantum cosmology, which tries to apply quantum principles to the universe as a whole. It asks how spacetime could emerge from quantum rules, or whether rules themselves require explanation. This is not merely abstract philosophy, because different proposals can leave different statistical fingerprints in primordial fluctuations. At this point, we need a careful definition of empty space, because it is not truly empty. In quantum field theory, a vacuum is the lowest energy state, filled with fluctuations and constrained by symmetries. Even when no particles are present, fields still have a ground state jitter that cannot be removed. Virtual particles, zero-point energy, and vacuum polarization are not metaphors in the equations. They are measurable effects, even if their interpretation is subtle. The Casimir effect, for example, shows that two uncharged metal plates can feel an attractive force because the vacuum's allowed modes change between them. So when physicists say something can come from the vacuum, they mean from a structured ground state. That is still a kind of something, and the distinction matters. A vacuum can have energy, obey conservation laws, and respond to gravity, features that pure philosophical nothingness would not possess. But the vacuum is also the closest thing physics has to an operational nothing. It is a baseline that can be probed, modelled, and tied to observation. When we strip away matter, heat, and radiation, we do not reach absolute absence, we reach a quiet, restless substrate. This chapter's job is to keep both truths in view without collapsing them into a slogan. Nothing in philosophy is not the same as vacuum in physics. If we confuse them, we may think we have answered the question, when we have only changed the definition. Now we tighten the timeline to the earliest moments that our evidence can touch. The cosmic microwave background shows conditions about 380,000 years after the hot beginning. That sounds late, but it is early in cosmic terms, long before the first stars ignited and long before galaxies settled into familiar shapes. Nucleosynthesis reaches back to minutes after, and particle physics extends our models to fractions of a second. Beyond that, we approach the Planck epoch, where quantum gravity becomes unavoidable. Each step backward increases the energy scale, and with it the risk that our trusted equations are incomplete. The Planck time is about 10 to the minus 43 seconds, a scale where spacetime may not behave smoothly. Our current theories cannot be trusted there, because we cannot yet unify gravity with quantum mechanics. At that boundary, the very notion of a continuous spacetime manifold may dissolve into something granular, probabilistic, or emergent. This is where the story becomes investigative rather than declarative. We shift from what we know to what we infer and to what we can test indirectly. The tone changes, less like reading a record, more like reconstructing an event from scattered traces. One major proposal is cosmic inflation, a brief period of accelerated expansion in the early universe. Inflation can explain why the universe looks flat, why distant regions share similar temperatures, and why primordial fluctuations have the patterns we see. In simple terms, it stretches a tiny, causally connected patch until it becomes enormous, smoothing curvature and diluting unwanted relics. Inflation also changes the origin question, because it can push traces of earlier conditions beyond our horizon. It can make the Big Bang look like a reheating event after inflation ends. Visually, the universe cools and empties during inflation, then floods again with particles and radiation as the inflationary field decays. Yet inflation raises its own questions about initial conditions and the field that drives it. It can also lead to eternal inflation, where inflation continues in some regions and ends in others. If that happens, the end of inflation becomes local, like bubbles forming in a boiling liquid, each bubble a region with its own hot beginning. That possibility opens the door to multiverse ideas, where our observable universe is one bubble among many. The multiverse is not a single theory, it is a family of outcomes from certain models. The scientific pressure point is not wonder, but inference. What counts as evidence when other regions may be causally disconnected? Some physicists see it as a natural extension of inflationary dynamics. Others see it as a retreat from testability, because other bubbles may be forever unobservable. The disagreement is not just about taste, it's about what standards cosmology should accept when direct experiments are impossible. Another set of ideas explores pre-Big Bang scenarios where the hot beginning is not the absolute start. These include bouncing cosmology's cyclic models and proposals from string theory. They keep the successful parts of the hot Big Bang while trying to replace the singularity with a transition. In a bounce, a prior contracting phase avoids a singularity and transitions into expansion. In cyclic pictures, the universe may go through repeated eras, with each cycle resetting conditions. The visual language here is rhythmic: contraction, compression, and then a rebound. Yet the physics must still explain how entropy, structure, and quantum fluctuations behave across the turnaround. There are also boundary-type models, where time behaves like a spatial dimension near the origin. In such cases, asking what happened before can be like asking what is north of the North Pole. The metaphor works because it replaces a sharp edge with a coordinate limit, an end to the question rather than an event that needs a cause. All of these ideas share a goal: to replace the singularity with a physical mechanism. They also share a problem, because evidence from such early times is hard to preserve. The early universe is a furnace that erases detail, and later cosmic evolution can blur whatever faint signatures remain, so we'll keep returning to one standard throughout the series. A good origin story must connect to observation, even if the connection is indirect and statistical. In cosmology, the data often come as distributions and correlations, patterns in the sky that must be compared to simulated universes. We will also keep returning to definitions, because the word nothing does too much work. If nothing means no space-time and no laws, physics may not be able to speak about it. A theory needs assumptions, and absolute nothingness offers no foothold for equations. If nothing means a quantum vacuum with laws, then universes might be possible, but the deeper question shifts. Why these laws, and why this vacuum, and why any framework at all? The mystery does not vanish, it moves one layer down into the origin of the rules themselves. This is not a failure of science, it is the edge of its method. Science explains within a set of assumptions, and the origin question presses on the assumptions themselves. That pressure can be productive, because it forces clearer definitions, sharper models, and more honest limits. Still, the Big Bang remains our best description of the early universe we can test. It is a theory of evolution from a hot, dense state, supported by redshifts, the microwave background, and primordial elements. It also integrates with general relativity and particle physics in a way that has survived decades of increasingly precise measurement. It is not yet a complete theory of creation, because it does not tell us why the initial state existed. It also does not tell us whether the initial state was truly first. The question of first may depend on whether time is fundamental, emergent, or simply the coordinate we use to track change. So the mystery is defined, and the stakes are clear. If the universe began, then time, space, and causality may have a boundary. That boundary would not be a wall in space, but a limit in meaning, where our ordinary intuitions stop working. If the universe did not begin in the usual sense, then our intuition about beginnings may be the wrong tool. Either way, the word nothing will need discipline. The more carefully we define it, the more clearly we see what physics explains and what it merely assumes. From here, we move from definitions to the earliest physics we can model. We step toward the Planck epoch, where quantum fluctuations and gravity collide, and where origin stories must earn their evidence. The darkness at the start is not just visual, it is epistemic, and our task is to see how far the light of observation can reach. Chapter 1 left us with a disciplined problem. Nothing, in philosophy, is not the vacuum of physics, and the difference is not cosmetic. In metaphysics, nothingness can mean the absence of laws, properties, and even possibility itself, an idea that resists measurement by design. In modern field theory, by contrast, a vacuum is a state, structured and restless, defined by equations and constrained by symmetries. That distinction matters because the Big Bang sits in the gap between meanings, powerful and incomplete, like a reconstruction with missing frames. It is the best supported account we have of the early universe's evolution, and it has survived a century of increasingly precise tests. Yet it does not automatically answer why there is a universe at all, or why the laws we use are the laws that hold. This chapter treats the Big Bang like a forensic reconstruction, careful, evidence-driven and suspicious of easy beginnings that arrive too neatly. We do not start with a mythic first moment or a dramatic explosion at a point, because that image misleads more than it clarifies. We start with signals that survive to the present, and we rewind only as far as physics allows, keeping track of every assumption. Imagine the opening visuals as a dark ocean of space, punctured by island galaxies, each one carrying a faint barcode of spectral lines. The camera drifts past spirals and ellipticals, and then the light is split into a rainbow band on a detector. Those lines are our first clue, because motion is written into light, and atoms leave signatures that are hard to counterfeit. When we split a galaxy's light into a spectrum, familiar atomic features slide toward longer wavelengths, as if the entire barcode has been pulled to the red. The shift is measurable with high precision, and it can be confirmed across different elements and different instruments. Even when the galaxy is too faint for detail, its spectral displacement still speaks. Distant galaxies show redshift, and the shift grows with distance, forming a pattern that becomes undeniable once you see it across thousands of objects. The simplest reading is expansion, not through space like shrapnel moving outward, but of space itself, changing the meaning of far as time passes. In this picture, galaxies are mostly not racing through a static void. Rather, the metric that defines distances is evolving. Historically, this clue arrived in pieces, and it did not feel inevitable at first, because the universe was once assumed to be eternal and largely unchanging. Vesto Slipher measured large redshifts before the 1920s, using painstaking spectroscopy that turned faint smudges into quantitative velocities. Edwin Hubble later connected distance estimates to those shifts, and the relationship transformed a collection of measurements into a cosmic law. Georges Lemaitre, working with general relativity, recognized that an expanding solution could unify the observations with theory, an audacious step when the idea of a dynamic cosmos still felt radical. The Hubble, Lemaitre law ties recession speed to distance, at least for relatively nearby galaxies where the relation is close to linear. The constant of proportionality, h0, is not just a number for today, and it is not merely a calibration detail for astronomers. It is a snapshot of the expansion rate at our cosmic time, and it becomes a lever for estimating the universe's age in broad terms. Behind that law is a deeper idea: homogeneity and isotropy on large scales, the assumption that the universe looks similar in every direction and from every location. That assumption is not a philosophical preference, because it is tested by surveys of galaxies and by the smoothness of the CMB. It is also encoded in the Friedmann-Lemaitre-Robertson-Walker metric, the mathematical scaffold that turns expansion into a precise statement. It is not a special direction or a central blast, and the data do not point to a privileged center. It is a uniform scaling, where every large region sees others receding, provided you average over local gravitational motions. From any galaxy, the sky would look broadly similar because the expansion is built into the metric that measures distance, not into a single explosive origin point. A useful visual is a grid drawn on a stretching sheet, where galaxies sit at grid intersections like pins on elastic fabric. As the sheet expands, the grid spacing grows, and every point sees every other point moving away in proportion to separation. No point is the centre of the expansion, even though every observer can feel like they are, because the pattern is self-similar. Redshift in an expanding universe is not only Doppler motion, though Doppler intuition helps at low redshift, where velocities can be treated in familiar terms. Wavelengths stretch as space-time stretches during the photon's journey, and the stretching accumulates gradually over billions of years. The light arrives older, longer, and lower in energy, its frequency reduced by the growth of the scale factor that measures cosmic size. That stretching is not a property of the source alone, and it is not a property of the detector alone, which is why it feels conceptually slippery. It is a property of the path between them, integrated over the changing geometry of the universe. The photon's energy is not lost into space like a leaking battery. Rather, energy conservation is subtler in a dynamic space-time where time translation symmetry does not hold globally. If distances grow today, then distances were smaller yesterday, and the logic is as simple as it is relentless. Rewinding the scale factor compresses matter and radiation together, and compression implies higher density, higher temperature, and faster interactions. Particles collide more often when space is tighter, and frequent collisions drive systems toward equilibrium, smoothing out many irregularities. This is the Big Bang model's first claim. The universe had a hot, dense early phase and has been cooling as it expands. Cooling here means that typical particle energies drop as the universe dilutes, and that radiation shifts to longer wavelengths. It does not yet claim what set that phase in motion, or why the initial conditions were what they were, and it does not pretend to answer metaphysical questions by default. We can test the rewind because expansion leaves multiple fossils, and the best reconstructions never rely on a single clue. Motion is one fossil, but it's not enough by itself, because distances are hard to measure, and local motions can confuse the picture. A forensic case needs independent lines of evidence, ideally with different systematics and different physical assumptions, so that agreement becomes meaningful. The second clue is a glow that comes from everywhere, a faint light that seems to fill the sky behind all galaxies. The cosmic microwave background, or CMB, surrounds us with near-perfect thermal radiation, and it is astonishingly uniform in every direction. It looks like a cooled remnant of a once blazing universe, now diluted into microwaves, and it behaves like a textbook blackbody. The discovery history adds weight to the clue, because it was predicted before it was seen, and the prediction was not vague. In the mid-20th century, theorists argued that a hot early universe should leave behind a relic radiation field, cooled by expansion but still present. When Arno Penzias and Robert Wilson detected an unexplained microwave hiss in 1965, they first suspected pigeons and electronics, because the signal was stubbornly isotropic. The hiss matched the prediction with uncanny precision, and the sky suddenly had a measurable afterglow. To understand the background, we need the early plasma, and we need to picture it clearly rather than romantically. In the first hundreds of thousands of years, electrons and nuclei were not bound into atoms because the temperature was high enough to keep matter ionized. The universe was filled with an ionized fog, and photons scattered constantly off free electrons through Thomson scattering. In practical terms, light was trapped in a bright churning medium, more like the interior of a star than empty space. In that era, light could not travel far without being redirected, so the mean free path of a photon was short. The cosmos was opaque in the same way the interior of a star is opaque, because radiation and matter were tightly coupled. Temperature was a shared property because matter and radiation exchanged energy efficiently, and the whole system behaved like a single fluid. As expansion cooled the plasma, protons captured electrons and formed neutral hydrogen and helium, and the balance tipped quickly once it began. This transition is called recombination, even though it was the first combination, an old name that stuck from earlier laboratory contexts. The key effect is that the number of free electrons dropped dramatically, and that change altered the universe's transparency, almost like a curtain lifting. With fewer free electrons, photons stopped scattering efficiently, and the radiation field began to stream rather than diffuse. That moment is decoupling, when radiation ceased to track matter's temperature closely, and the two histories diverged. The universe became transparent, and light began to travel freely, carrying a snapshot of conditions at that time: density, velocity, and temperature variations frozen into the radiation. Those photons are still arriving, but they have been stretched by expansion into microwaves. Their energy is reduced by the same scale factor growth that redshifts galaxies. Their spectrum is extraordinarily close to a perfect blackbody, with a temperature of about 2.7 Kelvin, and the deviations are tiny. That near-perfect thermal shape is hard to fake with later astrophysical processes, because stars and dust produce messy spectra, not pristine equilibrium curves. We do not see a single surface in space, like a wall at the edge of the cosmos, and the distinction matters for intuition. We see a last scattering surface, a spherical shell centered on every observer, defined by a time when the universe became transparent. It marks the farthest time we can see with light alone, because earlier than that the universe was effectively opaque, and photons could not carry information over long distances. A visual can make the geometry intuitive. Place an observer at the center of a transparent bubble, and draw a glowing shell around them. The camera rotates, and the shell remains centered, because it is not a physical object located out there. Wherever the observer moves, the shell moves too, because it is defined by time, not by location. The CMB is the edge of our electromagnetic visibility, not the edge of the universe. The background is almost uniform, and that uniformity is a clue with deep implications, because it is not guaranteed by expansion alone. It says the early universe was close to thermal equilibrium, meaning it had time to mix and smooth out temperature differences over large scales. It also says expansion was smooth on large scales, without giant primordial voids or clumps dominating the early sky. Uniformity is evidence of an early state that was both hot and well coupled, like a system that had time to settle. Yet the background is not perfectly smooth, and that imperfection is where the story becomes interesting, because structure needs a starting point. Tiny anisotropies appear at the level of tens of microkelvin, variations of only about 1 part in 100,000. On maps from COBE, Royal W Map and Planck, those ripples look like delicate mottling across the whole sky, a faint speckle pattern painted on a nearly uniform glow. Those ripples are not random static from an instrument, and their statistical properties are repeatable across missions and frequency bands. They're a map of early density variations and velocity flows, imprinted when photons last scattered, and they carry a characteristic angular pattern. In a sense, they are the earliest photograph we have, taken when the universe was about 380,000 years old, long before the first stars ignited. The anisotropies encode acoustic physics in the primordial plasma, and the mechanism is surprisingly concrete once you translate it into forces. Gravity tried to compress overdense regions, pulling matter inward and deepening potential wells. Radiation pressure pushed back because photons resisted being squeezed, and the result was oscillation, like a spring mass system driven by gravity and stiffened by light. These oscillations were literally sound waves, though the sound travelled through a plasma of particles and light rather than through air. Their speed depended on the mixture of radiation and baryonic matter, which sets an effective sound speed in the coupled fluid. Their characteristic scales depended on how far pressure waves could travel before decoupling, creating a standard ruler called the sound horizon. When the universe became transparent, the waves froze into a pattern of hot and cold spots, preserving a record of their phase at that moment. In the CMB power spectrum, that pattern becomes a series of peaks, each one a harmonic of the same underlying physics. The first peak corresponds to regions that had time to compress once, reaching maximum density at the snapshot. Higher peaks correspond to regions that completed more oscillations before the snapshot was taken, alternating between compression and rarefaction. The spacing and relative heights of the peaks are not arbitrary, and they encode the contents of the universe like a fingerprint. Those patterns are not decorative noise, they're a measurement tool that turns sky maps into numbers. They let us infer the universe's composition and geometry with remarkable precision, and they do it using linear physics that we understand well. They constrain the baryon density, the dark matter density, and the curvature of space, because each ingredient shifts the peaks in a distinctive way. Even the overall tilt of the spectrum reflects the distribution of primordial fluctuations across scales. Baryons add inertia to the plasma, enhancing compressions relative to rarefactions, so peak heights become a census of ordinary matter. Dark matter deepens gravitational wells without feeling radiation pressure, changing how the oscillations evolve and when they start. Curvature changes the apparent angular size of the sound horizon, bending the geometry of the sky's pattern and altering where the first peak lands. The fact that these inferences agree with other measurements is part of what makes the case compelling. The CMB also reveals the seeds of structure, and it does so with a quiet inevitability. Slightly denser regions later grew into galaxies and clusters, amplified by gravity over billions of years, while slightly underdense regions became cosmic voids. The background is a time capsule, but it is also an initial conditions report, an inventory of the tiny irregularities that would become everything we see. When you look at the mottling, you are looking at the blueprint of the cosmic web. A useful way to visualize that growth is to dissolve from a CMB map into a cosmic web simulation, matching the statistics rather than the exact pattern. The faint mottling becomes filaments and nodes, and then those nodes ignite into galaxies as gas cools and collapses. The camera can glide along a filament, showing clusters at intersections like dewdrops on threads. The universe's large-scale structure is in part the CMB grown up, shaped by gravity and the invisible scaffolding of dark matter. The third clue is chemistry, and it reaches earlier than the CMB, into an era where the universe was only minutes old. Big Bang nucleosynthesis happened when the universe was seconds to minutes old, after the earliest particle reactions had begun to settle. The temperature was high enough for nuclear reactions, but it was dropping quickly as expansion thinned the fireball, so timing mattered as much as physics. In that early interval, the universe was not yet a place of atoms and molecules, and it was not yet governed by chemistry in the everyday sense. It was a bath of protons, neutrons, electrons, neutrinos, and photons, all colliding at tremendous rates, with nuclear binding energies becoming relevant. The relevant physics is nuclear and weak interaction physics, not astrophysics in the usual sense, and the universe behaves like a reactor with a rapidly falling thermostat. At first, protons and neutrons interconverted through weak interactions, mediated by W and Z bosons, and equilibrium maintained a predictable ratio. Neutrinos played a central role, carrying away energy and helping maintain equilibrium among particle species, and then they gradually decoupled as the universe expanded. As expansion cooled the universe, those weak reactions froze out, because the interaction rate fell below the expansion rate, and the cosmic clock outran the reactions. The neutron-to-proton ratio then locked in, and neutrons began to decay with a half-life of about 10 minutes, steadily reducing the supply. That timing matters, because nuclear synthesis had to begin before too many neutrons disappeared, or helium production would be suppressed. The universe was racing its own clock, with expansion setting the pace and decay setting the deadline. It is one of the clearest places where cosmology and particle lifetimes intersect. At very high temperatures, deuterium could not survive, because energetic photons would break it apart as quickly as it formed. This is sometimes called the deuterium bottleneck, and it delays the start of efficient element building. Once the temperature fell enough for deuterium to persist, nuclear fusion proceeded rapidly, and the element building phase began in earnest. In a short window, the universe assembled its first nuclei and then moved on. Deuterium formed, then helium-3 and helium-4 accumulated, and the reaction network funneled material toward the most stable outcomes. Helium-4, with its tightly bound nucleus, became the dominant product, because it is energetically favoured and easy to build from available neutrons. A small amount of lithium-7 was produced through limited pathways, and even smaller amounts of other light nuclei appeared only fleetingly. The universe did not make heavy elements in this phase, because the density and time were insufficient, and stable mass 5 and mass 8 bottlenecks block easy pathways. The key outcome is simple and testable, which is why it is so powerful, and why it survives as a pillar. The early universe should be mostly hydrogen, about a quarter helium by mass, and trace deuterium and lithium, with abundances that can be calculated. The ratios depend on the baryon density and the expansion rate, because those parameters set reaction times and collision frequencies. They also depend on the number of light particle species, because extra radiation energy changes how fast the universe expands during nucleosynthesis. We measure these abundances in ancient gas and primitive environments, where stellar processing has been minimal, and the measurements are delicate. Astronomers look at absorption lines in the spectra of distant quasars, using intervening gas clouds as laboratories, and they compare multiple systems to control uncertainties. They also study metal-poor stars and ionized regions where primordial helium can be inferred, separating early universe production from later stellar enrichment. Each measurement is a small act of archaeology, reading chemical fossils in faint light. Deuterium is especially sensitive because stars destroy it rather than create it in bulk, so it functions like a one-way indicator. If you see deuterium today, it is often a relic, not a product, and its abundance points back to the density of ordinary matter. Helium-4 is robust because it is produced efficiently in the early fireball, and later also produced in stars, though the primordial fraction can still be estimated by extrapolating to low metallicity. Lithium is trickier because it can be created and destroyed in stars, and its surface abundance may not reflect its birth abundance cleanly. The agreement between prediction and observation is one of cosmology's strongest successes, and it is striking because it connects such different domains. It ties minutes-old physics to today's telescopes, linking nuclear reaction networks to faint spectral lines seen across billions of light-years. It also limits how much new physics can hide in that era, because changing early conditions would shift the abundances in ways we would notice. In that sense, the light elements are not just products, they're constraints. Yet the lithium problem remains a warning sign, a small crack in an otherwise clean wall, and it keeps the field intellectually honest. Observed lithium-7 is lower than simple predictions suggest, especially in old, metal-poor stars where primordial material should be most visible. The discrepancy may be astrophysical, involving stellar atmospheres, diffusion, and mixing that hide lithium from view, or it may hint at missing ingredients in early universe physics, and the fact that both possibilities remain open is itself instructive. Together, expansion, the CMB, and nucleosynthesis form a coherent reconstruction. They point to a universe that was once hotter and denser than anything we can create on Earth, and they do so with mutually reinforcing evidence. They do not by themselves identify an absolute beginning, because they describe evolution from an early state rather than creation of the state. The case is strong, but it is a case about history, not about metaphysical origin. Now we clarify common confusion, because language invites it and popular imagery amplifies it. The Big Bang model is a description of early evolution from a hot, dense state, supported by measurable relics. It is not automatically a claim about creation from nothing, and it is not a claim that the universe began as a point in ordinary space. The phrase Big Bang itself, coined in a critical tone, can smuggle in the wrong picture if we're not careful. In equations, we often label the earliest moment as t=0, and the label can look like a declaration. That label is a coordinate choice tied to the extrapolation of our models, and it is chosen for convenience when solving the equations. It is not a direct observation, and it is not necessarily a physical boundary in nature, because coordinates are not the same as events. General relativity, when run backward with ordinary matter and radiation, predicts a singularity in many simple cosmological solutions, and the mathematics is blunt. The scale factor shrinks towards 0, and curvature grows without bound, as if spacetime itself is being crushed. Density and temperature diverge in the simplest mathematical description, and geodesics can become incomplete, meaning the theory cannot extend trajectories further into the past. A singularity is not a confirmed object sitting somewhere in spacetime, like a point you could approach with a spacecraft. It is a signal that the theory is being pushed past its domain of validity, where neglected physics becomes dominant. Physicists treat it as a breakdown of classical spacetime, not a reliable description of reality, in the same way that infinite values in fluid equations can signal turbulence or missing microphysics. The singularity problem is therefore a clue, not a conclusion, and it points in a specific direction rather than toward a dramatic final answer. It tells us that gravity and quantum physics must meet, because classical gravity alone becomes internally inconsistent at extreme densities. It tells us that the Big Bang is evidence-based, but not yet complete, because the reconstruction ends where our tools stop working. This is where the word beginning becomes technical, and even a little slippery, because it can mean different things. Beginning can mean the earliest time our equations can describe with confidence, which is a practical boundary. It can also mean the first physical moment, if such a moment exists as an event in time, which is a deeper claim. The two are not automatically the same, and confusing them creates false certainty. If time itself is part of the system, then before may not be well defined, and that is not wordplay. Causality is usually a relation between events in time, with one event preceding another in an ordered sequence. Asking for a cause of time risks using the concept outside its range, like asking what is north of the North Pole. The question may still be meaningful in a deeper theory, but it cannot be answered by simply extending everyday intuition. So we proceed carefully and keep the reconstruction honest, even when the questions become tempting and the visuals invite drama. We can describe what happened after a certain threshold with high confidence, because multiple observations converge and the physics is tested. Earlier than that, we rely on high-energy physics and controlled extrapolation, and we must keep track of what is assumption. The frontier is not a failure, it is a boundary marker for knowledge. As we rewind toward earlier fractions of a second, the universe becomes a particle accelerator in every direction, with no walls and no off switch. Temperatures rise beyond billions of degrees, and matter exists in unfamiliar phases that do not appear in ordinary environments. The distinctions we rely on between particles, forces, and even vacuum states begin to blur, because high energies restore symmetries and populate many degrees of freedom. At around a microsecond, quarks and gluons were not confined into protons and neutrons, and the universe was a quark, gluon plasma. It was a dense soup of strongly interacting particles, where colour charges moved freely over short distances. In modern laboratories, heavy ion collisions briefly recreate similar conditions, offering a partial window into that epoch, and the comparison is one of the rare bridges between cosmology and experiment. As it cooled, confinement produced hadrons, and the familiar building blocks of nuclei emerged as quarks became bound into protons and neutrons. This transition is related to quantum chromodynamics, the theory of the strong interaction, and it involves a change in how degrees of freedom are organized. In the early universe, it was not a quiet phase change, but a cosmic reorganization of what counts as a particle. The vacuum structure of the strong force matters here, shaping how the plasma turns into matter. Even earlier, the electroweak force may have been unified, and the distinction between electromagnetic and weak interactions would not yet apply. At high energies, electromagnetism and the weak force behave as a single interaction, described by a unified gauge symmetry. Symmetry breaking later separated them and gave masses to W and Z bosons through the Higgs mechanism, changing the range and strength of weak interactions. In plain terms, the rules of force were simpler at high energies, and complexity emerged as the universe cooled. These statements are not speculative in the same way as creation from nothing, and that difference matters for credibility. They're extensions of tested particle physics into cosmic conditions, guided by accelerator results and well-verified quantum field theory. The uncertainty grows as we approach energies we cannot reproduce directly, and that uncertainty must be carried explicitly rather than hidden. Cosmology here becomes a careful negotiation between theory, data, and humility. One unresolved clue is the existence of matter itself, not just its distribution, and it is a clue that refuses to fade. The early universe should have produced matter and antimatter in nearly equal amounts, because high-energy processes tend to respect those symmetries. If the symmetry were perfect, they would annihilate, leaving mostly radiation and a universe without long-lived atoms. The fact that we are here means something broke that balance, but we live in a universe with a surplus of matter, and that surplus is measured with precision in the cosmic inventory. It shows up in the baryon to photon ratio, a tiny number that nonetheless determines whether galaxies can exist and whether chemistry can happen. Something in the early universe favoured matter over antimatter, and it did so consistently across the observable cosmos, leaving no large antimatter domains in our surveys. Baryogenesis is the name for mechanisms that could generate this imbalance, and it is constrained by clear requirements that are almost like a checklist. Any successful mechanism must satisfy conditions identified by Andrei Sakharov in 1967, and the conditions are demanding. It must violate baryon number, violate C and CP symmetries, and occur out of thermal equilibrium, so that the universe does not simply erase the imbalance as fast as it forms. We have evidence for CP violation in particle experiments, which means nature does distinguish between matter and antimatter in subtle ways. Yet the known amount of CP violation in the standard model appears too small to explain the cosmic surplus, at least in straightforward calculations. That mismatch keeps the question open, and it keeps the early universe relevant to particle physics, because the cosmos may have accessed processes our colliders have not. We have candidate processes in electroweak physics and beyond the standard model, including scenarios that add new particles or new phases that change the early thermal history. We do not yet have a confirmed origin for the imbalance, because the relevant energies and conditions are difficult to test directly. The matter-antimatter asymmetry remains a creation clue embedded inside early evolution, like a fingerprint without a known hand. This matters for the central question, because hot and dense is not the same as sufficient, and the difference is existential. If the Big Bang is a hot beginning, it still must explain why there is any persistent matter to build stars, planets, and observers. The asymmetry is small, but it is everything, because it is what remained after annihilation, the residue that became the material universe. As we rewind further, familiar concepts become less stable, and the narrator's language must become more careful, because metaphors start to break. At sufficiently high energy, particles are better described as excitations of fields, and the vacuum becomes a dynamical state with structure. Even the idea of a particle becomes frame-dependent and temporary, a useful approximation rather than a fundamental object. What we call empty space is a medium with quantum fluctuations and constraints. Gravity also becomes harder to ignore, because energy density is gravity in general relativity, and the early universe is saturated with energy. In the early universe, energy density is so high that spacetime curvature is extreme, and curvature feeds back into expansion. The geometry is not a passive stage, but an active participant in the dynamics, shaping how energy and momentum flow. When the stage itself moves, even defining energy becomes more subtle. At this point, we approach a boundary that has a name and a number, and the number is almost absurdly small. The Planck time is about 10 to the minus 43 seconds, a timescale so brief that ordinary language struggles to hold it. It is the scale where quantum effects of gravity are expected to dominate, because the characteristic energies approach the Planck energy. It is not a measured wall, but it is a warning sign posted by dimensional analysis and theoretical consistency. The Planck length is about 10 to the minus 35 meters, and it is equally hard to picture in any visual metaphor. It is not a proven minimum distance, and no experiment has directly measured such a limit, so it should not be treated as dogma, yet it marks where combining quantum mechanics and gravity yields strong fluctuations, suggesting that the classical idea of a smooth metric may fail. In plain terms, spacetime may not behave like a continuous fabric at that scale. In this regime, spacetime itself may fluctuate, and the phrase is not poetic, even if it sounds like it. The notion of a definite geometry could be replaced by a quantum superposition of geometries, where distance is not a fixed background quantity, but a probabilistic one. Our standard tools assume a background time, and that assumption may break when time is part of what must be quantized. The most basic coordinate on our graphs becomes part of the unknown. This is why t equals 0 is not a scientific statement by itself, and why we resist treating it like a photographed event. It is the limit of a classical extrapolation, not a measured moment, and extrapolations can fail abruptly when new physics enters. The closer we get, the more this stage becomes part of the mystery, and the less we can treat spacetime as an unchanging container. The equations are still useful, but they are no longer sovereign. The Big Bang, then, is evidence for a hot, dense, early universe, and the evidence is unusually diverse for a historical science. It is not yet a complete account of origins, because it does not tell us why those conditions existed, or why the laws take their observed form. It is a map that ends at a frontier where quantum cosmology must take over, and where the meaning of beginning may need revision. The frontier is not empty, and it is not merely ignorance because it has a specific shape defined by conflicting principles. It is a region where our best theories conflict in their foundations, even though both are extraordinarily successful in their own domains. General relativity demands a smooth spacetime, and quantum theory treats fields and states probabilistically, with uncertainty built in. The tension is not a gap in data alone, it is a mismatch in how reality is modelled. So we build suspense by naming what we can say with confidence, and by showing how that confidence is earned through independent tests. Expansion happened and continues, and it is measured in multiple ways across cosmic history, including redshift surveys and distance ladders. The universe cooled from a hotter state, leaving the CMB and light element abundances as records that still fill our instruments. We can even watch structure grow, matching simulations to the observed cosmic web. We also name what we cannot yet say, because honesty is part of the method and part of the tone. We cannot describe the Planck epoch with tested equations, and we cannot yet derive the initial conditions from first principles. We cannot decide whether there was a before with observational certainty, because our observational reach ends at the last scattering surface, and our theoretical reach ends earlier still. The darkness here is not failure. It is the edge of the flashlight. This chapter's conclusion is a shift in posture, not a retreat, and it is a disciplined kind of mystery. The Big Bang is not the beginning, at least not in the way the word suggests, with a clear first tick of time. It is the earliest chapter we can reconstruct with evidence, plus a boundary where our language fails and our equations demand a deeper framework. The model is strong where it is tested and silent where it must be. Together, these pillars tell a consistent story of a universe that was once hotter and denser, and they do it without appealing to myth. From here, we move from definitions to the earliest physics we can model, guided by particle theory and constrained by observation. The case file is strong, but it is not complete, and the missing page is exactly where the deepest questions live. What, if anything, does it mean for a universe to have an origin in time? In the next chapter, we step into the proposals that try to replace the singularity, and we ask what it would mean to do cosmology without a classical spacetime background. We ask how quantum rules might generate spacetime, and what nothing could mean at the Planck boundary, when even geometry may be uncertain. The evidence points backward with clarity, yet the first moment, if it exists, still hides behind the frontier, waiting for a theory that can speak without breaking. We have a reliable story for a hot early universe, supported by multiple fossils in the sky and in matter. The cosmic microwave background glows like cooled embers, and its near-perfect black-body curve reads like a thermometer left behind by the primordial fire. Light element abundances read like a chemical receipt from the first minutes, because nuclear reactions in the early plasma lock in ratios of hydrogen, helium and lithium. Yet the story ends at a frontier where the equations demand a deeper language, because the tools we trust begin to contradict each other. The closer we rewind, the more the stage itself becomes part of the plot. In visuals, the familiar timeline compresses until labels crowd together, then blur, then vanish into a bright, unreadable band. Galaxies dissolve into plasma, plasma into fields, and fields into something we cannot draw with ordinary coordinates or even ordinary intuition. The camera keeps pushing inward, as if zooming through the fabric of the universe, until even the notion of fabric becomes a guess. What remains on screen is motion without landmarks, an expanding glow where the usual grid refuses to hold. The Planck epoch names that frontier not because we have observed it, but because our theories point to it as a limit. It refers to times earlier than about 10 Noah 43 seconds, when energies approach the Planck scale and the relevant lengths approach 10 Noah 35 meters. Those numbers are not arbitrary milestones, because they are built from the constants that set nature's basic conversion rates. At that scale, gravity cannot be treated as a smooth classical field, because quantum effects should dominate and back reaction becomes unavoidable. The Planck scale is built from constants that define how nature measures action, light and gravity, and the combination is strikingly rigid. Combine Planck's constant, the speed of light, and Newton's constant, and a new set of units appears, as if the universe hands us its own ruler. The Planck length, time, and energy are not special by decree, because they mark where our separate theories collide. Those units indicate where quantum uncertainty and gravitational curvature become equally important. So the usual separation between matter and geometry starts to fail. It helps to say this in plain terms, because the symbols can hide the meaning behind impressive exponents. Quantum mechanics tells us that trying to localize energy too sharply forces fluctuations, and those fluctuations become more violent at smaller scales. General relativity tells us that energy curves spacetime, and enough energy packed into a small region can form a horizon. At the Planck scale, the act of probing spacetime risks creating the very gravitational distortion that ruins the probe. Measurement becomes part of the phenomenon. In ordinary conditions, spacetime behaves like a stable background, and quantum fields fluctuate on top of it like ripples on a calm lake. In a particle accelerator, we treat the geometry as fixed, then compute probabilities for scattering and decay with exquisite success. In general relativity, spacetime is not a background at all, because geometry responds to energy and momentum, and can carry waves of its own. In quantum mechanics, time is usually an external parameter that tells the wave function how to evolve, even though that assumption is rarely stated aloud. That mismatch is not a philosophical quibble, because it blocks a clean merger of the theories when we push them into the same regime. In relativity, time is dynamical and tied to the metric, so it can stretch, warp, and even slow near massive bodies. In quantum theory, time is often assumed rather than derived, and it sits outside the system like a metronome. When we attempt to quantize gravity in the same way we quantize other forces, the mathematics tends to produce infinities that refuse to cancel, as if the theory is warning us that the setup is wrong. Historically, this tension has been visible for almost a century, even as each theory succeeded spectacularly in its own domain and reshaped the modern world. Einstein's general relativity, published in 1915, replaced gravity as a force with gravity as geometry, and it quickly explained Mercury's orbit and the bending of starlight. Quantum mechanics, assembled in the 1920s, explained atoms, chemistry, and the stability of matter, while also insisting on uncertainty and probability. Both frameworks are tested to astonishing precision, yet their underlying assumptions about time and measurement do not line up. The triumphs make the conflict sharper, because we cannot dismiss either side as merely approximate. So when we ask what happened at the beginning, we immediately collide with a deeper question that sounds grammatical, but is actually physical. What does before mean if time is part of what must be explained, rather than a container we can take for granted? A cause is normally an earlier event, and the earliest moment challenges the grammar of causality. Even our verbs, begin, proceed, emerge, smuggle in a timeline that may not exist in the usual way. The closer we get to the origin, the more language itself starts to wobble. The Planck epoch is therefore a shoreline of knowledge, where intuition fails and definitions become unstable under pressure. It is not simply very early, because it may be a regime with different basic ingredients and different bookkeeping. The concept of a smooth spacetime manifold may be an approximation that breaks at tiny scales, the way a calm ocean surface hides molecular motion. We can still describe waves from far away, but the closer we look, the more the surface becomes a swarm. In that swarm, here and there may not be sharply separable. One way to say it is that spacetime itself may fluctuate, not just the fields that live within it. If geometry is quantum, then distance and duration can become uncertain, not merely hard to measure with imperfect instruments. The uncertainty would be intrinsic, because the metric itself would be subject to quantum indeterminacy and cannot be assigned a single exact value. The universe could be described by a superposition of geometries rather than a single definite metric, and classical spacetime would be what emerges when that superposition effectively narrows. Imagine the visual language this demands, and why ordinary diagrams begin to feel dishonest. A clean grid of coordinates, the kind used in textbooks, begins to shimmer, then buckle, then fragment into a restless haze. Lines that once marked equal seconds and equal meters no longer stay parallel because the meaning of equal is no longer fixed. The camera tries to focus, but the scene refuses to settle into one geometry, as if the lens itself were made of uncertainty. Physicists sometimes call this possibility quantum foam, a shorthand for violent microscopic fluctuations and a reminder that smoothness may be a macroscopic illusion. The phrase comes with history, associated with John Wheeler and his attempt to picture spacetime at the smallest scales. It is suggestive, but it is not a settled prediction, and it risks sounding more certain than it is. It captures the idea that at extreme energies, spacetime might not be smooth, even in principle, and that empty space could be dynamically restless. In Wheeler's original spirit, the foam is not just bumpy geometry, but a churn where topology itself might flicker from one configuration to another. Tiny wormhole-like connections or transient horizons are sometimes invoked as metaphors for what quantum gravity could allow, yet the documentary must hold the line between illustration and claim. These are images for intuition, not confirmed features of our universe. The honest point is simpler. The classical notion of a single continuous geometry may fail, and with it our usual idea of a single continuous history. Another possibility is discretized geometry, where space and time come in smallest units that cannot be subdivided without losing meaning. In such pictures, areas and volumes might be quantized, like energy levels in an atom, so that geometry has a granular spectrum. The goal is not to add science fiction pixels, but to build a quantum theory that avoids infinities by limiting how finely the world can be divided. A minimum length is a way of saying that the continuum is an approximation, not an axiom, and that the smooth line of calculus may be a high-level summary. Discreteness also changes what we mean by smooth, and the change is subtle enough to hide in plain sight. A circle can look smooth from far away, yet be made of tiny steps when magnified enough. Likewise, a spacetime that appears continuous at human scales could be built from elementary chunks that only reveal themselves near the Planck length. The question is not whether our eyes would see the steps, but whether the mathematics demands them to remain consistent and free of contradictions. A third possibility is more radical, and it changes what we mean by nothing by changing what we mean by space. Spacetime might be emergent, arising from deeper quantum degrees of freedom that are not themselves geometric. If that is true, then the beginning is not a moment inside spacetime, but a transition into spacetime. The place where the universe begins would not be a location, because location is part of what emerges. The origin would be less like a first frame of a film, and more like the moment the screen itself turns on. This idea has a familiar analogue in other areas of physics, and the analogy is worth lingering on because it is both technical and intuitive. Temperature feels fundamental in daily life, yet it emerges from the collective motion of molecules, and it disappears when the system is too small. Pressure, viscosity, and fluid flow behave similarly, obeying effective laws that break when the microscopic description takes over. If spacetime is like that, then geometry is a large-scale summary of something deeper, and the Planck epoch is where the summary stops being reliable. These ideas do not form one theory, and that matters for honesty and for the tone of this chapter. Quantum cosmology is a toolkit, a set of approaches that try to quantize the universe's earliest description, without pretending we already know the right foundations. Some approaches start with a wave function of the universe, and others start with discrete building blocks that approximate geometry at large scales. Each approach chooses a language, then tests whether that language can reproduce known physics, because any credible beginning must connect to the universe we actually observe. All of them face a shared problem, sometimes called the problem of time, and it is more than a technical nuisance. If the universe is the whole system, there is no external clock to refer to, and no outside observer to define a measurement in the usual way. The usual Schrödinger picture assumes a time parameter, but quantum gravity may not allow one as a fundamental input. We are used to asking how a system changes in time, yet here time is part of the system, and it may have to be reconstructed rather than assumed. In canonical quantum gravity, the basic equation often looks timeless, like a constraint rather than an evolution law, and that can feel like a paradox. The Wheeler-DeWitt equation is the famous example, where the wave function does not change with an external time variable. Instead, it encodes relationships among possible geometries and matter configurations, like a catalogue of consistent universes. Time must then emerge from correlations between parts of the system, not from an outside tick, and evolution becomes a statement about internal comparison. This is a subtle shift, and it can sound abstract until we translate it into ordinary physical reasoning. A clock is just a physical subsystem that changes in a regular way, and we use it to label other changes. If no external time exists, we can still compare one changing subsystem to another and call that comparison time. In that sense, time becomes relational, an ordering of correlations rather than a universal background. The question then becomes, which correlations are stable enough to serve as time when the universe is still quantum? This is where the singularity returns, not as a dramatic point, but as a warning sign that the classical story is being pushed past its domain. In classical general relativity, running the expansion backward leads to diverging curvature and density, and geodesics can become incomplete. The singularity theorems developed by Hawking and Penrose in the late 1960s showed that under broad conditions a singularity is hard to avoid classically. Yet those theorems also assume classical spacetime, and they do not include quantum effects, which is exactly what the Planck epoch demands. A singularity is what a theory produces when it is asked a question it cannot answer, and the failure is mathematical before it is physical. It is the map's edge, where the assumptions used to draw the map fail. The Planck epoch is the region where we expect those assumptions to fail first, because quantum fluctuations and gravitational back reaction become inseparable. The divergence is less a prediction of infinite stuff, and more a signal that the variables have stopped making sense. It is a red warning light on the dashboard, not a photograph of the engine. So the question becomes precise and unsettling. and it refuses to be satisfied by slogans. Is the Big Bang singularity a real beginning, or a sign that classical spacetime is the wrong language for the earliest regime? If quantum gravity replaces the singularity with a finite process, the universe may not start at a sharp edge. The beginning might be a transition, a rounding off, or a bounce, depending on the deeper rules and on what counts as earlier when time itself is under construction. Stephen Hawking pushed this line of thought into a concrete proposal, and he did it with the same mix of audacity and restraint that marked his career. With James Hartle, he suggested the no-boundary idea, a way to describe the universe without a temporal edge where the equations break. The proposal uses quantum cosmology to treat the earliest region as smooth, not abruptly beginning. It is an attempt to replace initial conditions at a singular point with a self-contained quantum description, where the universe is specified by a condition of regularity rather than a moment of creation. The key move is to change how time behaves near the origin, not by hand-waving, but by changing the mathematical role it plays. In the no-boundary picture, time can act like a spatial dimension in the earliest regime, in a mathematically controlled way. Instead of a first moment, the geometry rounds off, like a surface with no boundary. In the visual language, the timeline does not start with a jagged cut, but curves into a closed cap, and the camera glides over it without encountering an edge. This is not a claim that the universe has no history, or that nothing happens near the beginning in any meaningful sense. It is a claim that the beginning may not be a point in time, the way our intuition demands. The question, what happened before, may become undefined, not merely unanswered, because before presumes a time direction already in place. That is a hard thought to hold, because our minds are trained to look for earlier causes, and the training is reinforced by every story we have ever told. The proposal is often explained with a simple analogy, but the physics is more careful than the metaphor suggests. A sphere has no edge, yet it is finite, and you can travel without meeting a boundary. Hawking's idea tries to give the universe a similar kind of beginning, smooth rather than singular. The analogy is not meant to say the universe is literally a sphere in time, but to suggest how a boundary can be absent while the description remains complete. To make the image vivid, picture a two-dimensional surface that narrows toward a pole under soft, even lighting. As you approach the pole, the latitude circles shrink until they vanish, yet no cliff appears and no tear opens in the surface. In the no-boundary picture, the early universe behaves like that. Geometry closes gently rather than breaking. The mathematics uses a change in signature, but the narration can keep the intuition. The beginning is rounded, and the sharp edge is replaced by a smooth limit. No boundary is not confirmed, and it is not the only option, which is why it belongs here as a possibility rather than a conclusion. It is one attempt to compute probabilities for different early universes using a path integral approach, summing over possible geometries. The challenge is connecting such probabilities to observations in our universe, rather than to aesthetic preference. A proposal is only as strong as the signatures it can, in principle, leave behind, even if those signatures are statistical and indirect. This is where quantum cosmology becomes a discipline of constrained imagination, and the constraints are not negotiable. A good proposal must reduce to general relativity and quantum field theory, where those theories work, because we have tested them in their proper domains. It must also suggest signatures, even statistical ones, that could be compared with data. In practice, the data often come in the form of patterns, not photographs, spectra, correlations, and distributions. The universe speaks in statistics when the beginning is hidden. At the Planck epoch, even the word vacuum needs careful handling because it carries technical assumptions that can quietly slip by. In quantum field theory, the vacuum is not empty because fields have a ground state with fluctuations that cannot be switched off. The vacuum is the lowest energy state, but it still contains activity that is built into the uncertainty principle. If you try to remove all motion from a field, you run into the fact that the field and its conjugate momentum cannot both be fixed. So, stillness becomes impossible in principle. Those fluctuations are not merely a story we tell to make the math sound intuitive, and they are not confined to the blackboard. They produce measurable effects like the Casimir force between conducting plates, where the allowed modes of the electromagnetic field are restricted. They also show up in how particles and fields behave, through vacuum polarization and zero-point energy corrections. The vacuum, in other words, is a physical state with consequences, not a philosophical blank. Even when nothing is happening, something is being permitted. Vacuum energy matters in cosmology because energy gravitates, and gravity is indifferent to whether energy comes from particles or from the ground state. In general relativity, a vacuum energy acts like a cosmological constant, affecting expansion by contributing a uniform energy density with negative pressure. In quantum theory, vacuum energy is tied to the ground state, and it appears unavoidable in naive calculations. When you sum the zero-point energies of modes, the result is formally enormous unless some mechanism cancels it, and the scale of that mismatch is a clue that we are missing a principle. This creates a bridge to later chapters, because vacuum energy can drive accelerated expansion and can shape the growth of structure. It also creates a problem, because the observed cosmic acceleration is tiny compared to many theoretical expectations. The mismatch is one of the deepest puzzles in fundamental physics, because it is not a small discrepancy but a staggering one. It suggests that our understanding of vacuum, gravity, or both is incomplete, and that the Planck epoch may hold the missing piece. Still, the conceptual point is clear and essential for the central question, and it is worth stating without hedging. If nothing means a quantum vacuum, then nothing is not featureless. It has laws, structure, and a baseline energy that can influence geometry. Even emptiness in this sense is a kind of medium, defined by the equations that describe it. The vacuum is not an absence of rules, but a particular way rules express themselves. But if nothing means no space-time and no fields, then even the vacuum is too much, and the word starts to slip. A vacuum assumes a framework in which a lowest energy state is defined, and it assumes degrees of freedom that can fluctuate. It assumes equations, symmetries, and a notion of possibility. So we have to ask what we are allowed to keep when we say nothing, and what we have quietly smuggled in. The most dangerous assumptions are the ones that feel too basic to mention. This is why debates about universe from nothing often turn on definitions, even when they sound like debates about physics. Popular claims can quietly replace philosophical nothing with a physical vacuum, then treat the swap as if it were trivial. The swap can be useful, because physics needs a state to calculate with, but it must be stated. Otherwise, the argument changes the question while pretending to answer it, and the mystery is solved only by renaming it. In the Planck epoch, the vacuum may not even be well defined in the usual way, which makes the language even more delicate. The concept of a field living on a fixed space-time background may break down, because the background is no longer fixed. If space-time is quantum, then the vacuum state of fields may depend on the geometry that is itself fluctuating. The lowest energy state becomes ambiguous when the notion of energy depends on time translation symmetry, and time is not settled. Even the word ground starts to lose its footing. So we are forced into a more delicate picture, where the earliest universe is described as a coupled quantum system. The earliest universe may be described by a quantum state that includes geometry and matter together, rather than separating them into stage and actors. The stage and the actors become one coupled system, and neither is fully defined without the other. In a sense, the universe is describing itself, using variables that only become classical later, when decoherence and expansion make certain histories stable. This is the heart of quantum cosmology as a toolkit, and it explains why the chapter keeps returning to limits and definitions. It tries to describe the universe without assuming an external time or a pre-existing arena, because those assumptions are exactly what fail at the frontier. It asks for a law of the whole, even when the whole includes the coordinates we normally use. That is a demanding request, and it explains why the field contains multiple approaches rather than one finished answer. The frontier is crowded with partial maps. Different candidate frameworks attempt this in different ways, and each carries a distinct intuition about what is fundamental. Some quantize geometry directly, turning the metric into an operator with uncertainty and treating curvature as a quantum variable. Others replace geometry with discrete networks or algebraic structures, hoping space-time emerges at large scales as an effective description. The shared ambition is to recover the smooth world we see, while remaining consistent at the smallest scales. The test is whether the familiar world can be derived, not merely assumed. In loop quantum gravity, geometry can become quantized, with discrete spectra for area and volume, and that discreteness is meant to be physical rather than merely computational. In some models, the Big Bang singularity is replaced by a bounce, where contraction transitions into expansion as density reaches a maximum. These results are suggestive, but they depend on assumptions about symmetry and matter content, because exact calculations are difficult. The bounce is not a cinematic reversal, but a mathematical statement about finite curvature in certain settings, where quantum geometry provides an effective repulsion at extreme density. If we visualize such a bounce, the scale factor shrinks like a breath drawn inward, then pauses at a smallest size, then expands again into a widening cone of light. The picture is compelling, yet it raises immediate questions about what came before and how entropy and structure behave across the transition. A bounce can remove an infinity, but it does not automatically supply a complete origin story. It changes the edge of the map, then asks us to redraw what lies beyond, and to explain why the pre-bounce state had the properties needed to produce our universe. In string theory, spacetime can also behave in unfamiliar ways at high energy, and the unfamiliarity is built into the theory's basic objects. Extra dimensions, dualities, and extended objects can soften singularities in some settings, because strings do not probe points the way particles do. Certain dualities suggest that very small distances can be equivalent to larger ones, which changes how approaching zero behaves. The theory offers mechanisms for emergence, but connecting them to our universe remains difficult, and the space of possibilities is vast enough to be both a strength and a challenge. Even outside name programs, the recurring theme is the same, and it is the theme this chapter keeps circling. Classical spacetime may be an emergent approximation, like fluid behavior emerging from molecules, and it may fail when the microscopic description takes over. If so, the Planck epoch is where the molecular description matters, and the smooth picture fails. The universe at that stage may be more like a quantum many-body system than a classical arena, with collective behavior that only later looks like geometry. This reframes the singularity as a diagnostic, and diagnostics are valuable precisely because they tell us where to stop trusting our habits. The singularity may be telling us that we used the wrong variables, not that nature contains literal infinities. The boundary is not necessarily a physical point, but the edge of a classical coordinate system. In that sense, the singularity is less a feature of the universe than a feature of our description. The question becomes, what replaces coordinates when coordinates are no longer fundamental? Yet we should not pretend that replacing the singularity automatically explains the origin, because the oldest question is more stubborn than a divergence. A bounce still needs an account of why a prior phase existed and what set its conditions. An emergent spacetime still raises the question of what the underlying degrees of freedom are and why they exist. Removing a mathematical divergence is progress, but it is not the same as answering the oldest question. It is like repairing a compass without yet knowing where the coastline begins. The central question remains, but it becomes sharper, and it starts to sound almost like a challenge to the meaning of explanation. How can space-time, matter, and energy begin from nothing if even the vacuum is something? What would it mean for the laws that define the vacuum to exist without a universe? Are laws descriptions of patterns we observe, or are they ingredients that can operate in the absence of anything to observe? If the laws are real in that stronger sense, then nothing may already be ruled out by the existence of law. At this point, the documentary shifts from reconstruction to inference, and the shift is visible in the visuals as well as the logic. We cannot see the Planck epoch directly, but we can ask what traces it might leave, because later physics can preserve early fingerprints. The earliest quantum state could imprint statistics on later fluctuations, which later become patterns in the CMB. The sky, in this view, is a screen that still carries the grain of its earliest conditions. We read it the way geologists read layers of rock, by patterns, not by eyewitness accounts. This is why vacuum fluctuations matter beyond philosophy, and why they keep returning in cosmological storytelling. In inflationary theory, quantum fluctuations are stretched into cosmic scales, becoming the seeds of structure and the scaffolding for galaxies. Even if inflation is not the final story, the mechanism shows how microscopic quantum noise can become macroscopic reality. It turns randomness into a pattern, and it turns tiny uncertainty into a map of the large-scale universe. The astonishing part is not that fluctuations exist, but that expansion can preserve them as a fossil. When we look at CMB anisotropies, we are not seeing the Planck epoch directly, but we may be seeing its descendants in statistical form. The spectrum of fluctuations, their near-scale invariance and their phase coherence are clues about the processes that amplified them. The question is whether those clues can ever discriminate among quantum gravity beginnings, or whether they mostly reflect later dynamics. That uncertainty is part of the mystery, and it keeps the frontier honest. because it reminds us how easy it is to overinterpret a pattern. So we build a careful tension, and we let the camera linger on the boundary between what is drawn and what is inferred. If spacetime can fluctuate, then a sufficiently large fluctuation might do more than create particles within spacetime. It might create a region of spacetime itself, a bubble with its own internal time and its own causal structure. The idea is not that something pops into a pre-existing void, but that the void is part of what is being questioned. The fluctuation would be a change in the very conditions that define what a region is. This is the root of universe from nothing claims in modern physics, and it is why the claims must be handled with exacting care. They often rely on quantum tunneling or spontaneous creation from a vacuum-like state, described by a wave function and a probability amplitude. The claims require a framework with quantum laws, a notion of probability, and a definition of what counts as a state. In other words, they require a substantial amount of structure before the word nothing can do any work. The question then becomes whether that structure is a background assumption or an explained outcome. Quantum tunneling is familiar in particle physics, where systems cross barriers they cannot classically overcome, and the mathematics is precise even when the intuition is strange. An electron can appear on the far side of a potential barrier, not by climbing over it, but by having a non-zero amplitude to be found there. In cosmology, the barrier could be between no classical spacetime and a small universe that can then expand. The mathematics can be written, but the interpretation is subtle, because the usual time parameter is missing, and without time the word event becomes slippery. Some proposals treat the universe's beginning as a tunneling event from a boundary condition, where the wave function assigns amplitudes to different geometries. Others treat it as a no-boundary smoothing that removes the barrier language, replacing it with regularity conditions. Either way, the beginning becomes a quantum transition, not a classical explosion. The Big Bang, in this framing, is not a fireball at a point, but the onset of a classical regime, when one history becomes dominant enough to look like a single spacetime. Yet we must keep the limits visible, because mystery becomes propaganda when it pretends to be settled. We do not have a complete quantum gravity theory confirmed by experiment, and we do not have direct access to Planck-scale processes. We cannot yet compute unique predictions that separate these proposals cleanly, though some may differ in their expected fluctuation spectra. At present, the frontier is defined as much by what we cannot calculate as by what we can imagine. The honest narration keeps the fog in frame, so the Planck epoch remains a foggy shoreline, not a mapped continent, and the best we can do is mark the rocks we keep hitting. We can name what must be true if our current principles hold, even if we cannot write the final equations. Gravity must be quantum, spacetime may not be fundamental, and time itself may be emergent from deeper relations. The closer we get to that shoreline, the more our everyday categories begin to dissolve, and the more the universe looks like a question asked in its own language. This is also where the word nothing becomes most dangerous and most interesting, because it tempts us to treat a technical state as a metaphysical void. If spacetime is emergent, then nothing might mean the absence of classical geometry, not the absence of underlying quantum structure. The question becomes whether that underlying structure deserves the name something, or whether it is a new category that our language has not learned. When we say nothing, are we naming an absence, or are we naming a limit of description? And if it is a limit, what does it say about the kind of answers we should expect? Physics may not answer why there is something rather than nothing, at least not yet, and perhaps not in the way philosophy hopes, but it can show that the boundary between absence and existence is not inert, because quantum theory makes even ground states active. The quantum view makes the boundary structured, probabilistic, and potentially creative, though always within a framework of laws. That last clause matters because laws are not nothing, and the existence of law may be the deepest assumption of all. We end this chapter with a disciplined cliffhanger, and we keep the camera fixed on the place where the map turns blank. If the earliest regime is quantum, then the universe could begin as a quantum event rather than a classical moment, and the singularity may be replaced by a finite transition. But such claims require assumptions about laws, states, and what we mean by nothing, and those assumptions must be named. From here we move to the proposals that claim the most, and we test what they actually require. If a quantum fluctuation can seed an entire universe, what counts as the vacuum it fluctuates from? And if the vacuum is already something, what is left of the word nothing? We have pushed back to the Planck frontier, where spacetime itself becomes uncertain and the familiar stage of physics begins to blur. The closer we move toward that boundary, the more our everyday categories fail. Space, time, and even existence stop behaving like solid nouns. At those scales, the concepts that feel automatic in daily life become provisional, and physics starts speaking in probabilities instead of pictures. Now we confront the phrase that keeps returning in public science: universe from nothing. In everyday speech, nothing means empty space with the lights turned off, a perfectly blank room with no air and no dust. It suggests the absence of objects, the absence of activity, and the absence of any hidden bookkeeping. The camera can linger on a silent, unlit chamber, where even the sound seems to die. An image that feels intuitive, and therefore dangerously persuasive. In fundamental physics, nothing is often a technical state with structure, rules, and measurable consequences. This chapter makes that difference explicit because the argument turns on it, and the visuals can easily mislead. The word is the same, but the referent changes, and modern cosmology lives in that gap. A quantum vacuum is not a void with no ingredients, and it is not merely space without matter. It is the lowest energy state of quantum fields that fill all of space, even when those fields are not producing particles. Those fields are not optional decorations on space. In the standard model, they are what space is permeated with, everywhere and always. In modern physics, fields are the primary actors, and particles are what we notice when fields are excited. The electron is not a tiny bead that exists independently of everything else. It is a localized excitation of the electron field. In the same way, photons are excitations of the electromagnetic field, and quarks are excitations of their own fields, bound by the gluon field's dynamics. Quantum field theory treats particles as excitations, like ripples on underlying fields, and that analogy is more than poetic. Remove the ripples and you still have the water, and remove the particles and you still have the fields. Even when detectors register nothing, the fields remain as a set of degrees of freedom with a definite quantum state. The vacuum, then, is the calmest state available, not the absence of the ocean. It is a state defined by the theory's equations, symmetries, and boundary conditions, and it is as real as any other state. In practice, it is defined operationally by what it does to measuring devices, how it shifts energy levels, modifies forces, and constrains what can happen. Visually, imagine a dark screen that is not truly black but faintly alive with grain, subtle, restless texture that never freezes. The vacuum is quiet, but it is not still. If we overlay a transparent lattice, the lattice itself seems to shimmer, hinting that empty is a state with internal motion. This matters because the vacuum has energy, at least in the way the theory counts it and in the way experiments can sometimes reveal its effects. Ground states carry zero-point fluctuations that cannot be eliminated, even in principle. The phrase 0 point is literal. Even at the lowest allowed energy, the system does not sit at perfect rest. The reason is not a technical loophole but a foundational constraint. The uncertainty principle prevents a field and its conjugate momentum from both being perfectly fixed. So a perfectly motionless field is not an allowed quantum state. In plain language, the vacuum cannot be a perfectly flat line on every possible graph, because quantum rules forbid that level of exactness. So the vacuum is restless in a precise sense, even if it looks empty to our eyes. The field values fluctuate around their minimum, even at absolute zero temperature, because zero temperature does not mean zero quantum uncertainty. Temperature measures thermal agitation, but the vacuum's agitation is built into the structure of quantization itself. A useful way to say it is that the vacuum is the minimal jitter the universe permits. It is the baseline noise floor of reality, not because nature is sloppy, but because quantum structure is strict. That strictness is mathematical, yet it has physical consequences that show up in laboratories and in cosmological models. If we could zoom in with an impossible microscope, the image would not show particles flying around like sparks. It would show correlated fluctuations, patterns in the probabilities that link one region of space to another. The correlations are the key detail, because they tell us the vacuum is not mere randomness, but a structured quantum state. People often describe these fluctuations using the language of virtual particles, and that language can be helpful for intuition. Yet it can also mislead, because it invites a cartoon of tiny balls popping in and out like fireworks in empty space. The documentary can briefly show that cartoon, then peel it away, revealing the more accurate picture of fields and amplitudes. In many calculations, virtual particle is a bookkeeping device inside a perturbation series, not a claim about directly observed objects. It labels internal lines in Feynman diagrams, and those diagrams are a compact way of organizing terms in an expansion. Virtual particles can have off-shell energies and momenta, which is a technical way of saying they are not constrained like real, detectable particles. A Feynman diagram is not a literal photograph of what happens between two detectors. It is more like a map of contributions to an amplitude, where the measurable content appears only after you sum the possibilities and square the result. The diagram is a language for calculation, and the physics emerges from the whole sentence, not from a single word. That measurable content shows up in scattering rates, energy shifts and forces, where the vacuum's influence becomes operational. When the numbers match experiments, the vacuum stops being philosophy and becomes physics you can calibrate. The camera can shift from abstract diagrams to real instruments, metal chambers, lasers, vibration isolation, where nothing is treated as a controlled experimental condition. Still, the vacuum structure is not only metaphor, and it is not a story we tell only because we like the sound of it. It can leave physical fingerprints that experiments can test, and those fingerprints anchor the chapter. The point is not that emptiness is magical, but that emptiness is a state with constraints. The most accessible anchor is the Casimir effect, because it turns an abstract idea into a force you can measure. It also gives the camera something simple to show: 2 plates, a narrow gap, and a tiny push. This is the kind of phenomenon that makes audiences lean forward, because it looks like a trick until you explain the rules. Place 2 conducting plates close together in a vacuum, separated by a distance small enough that quantum modes notice the confinement. The allowed electromagnetic modes between the plates differ from the modes outside, because conductors impose boundary conditions on the field. The plates force the electric field to vanish at their surfaces, and that restriction changes what fluctuations are permitted. Between the plates, only certain wavelengths fit, like notes on a string fixed at both ends. Outside, the spectrum is richer, and that imbalance changes the vacuum energy density on each side. The effect is not that the plates create energy, but that they reshape the ground state by changing the set of allowed field configurations. The result is a tiny force pushing the plates together, and it grows stronger as the separation shrinks. In the lab, it is measured with delicate setups, torsion balances, micro-cantilevers, and surfaces polished to reduce stray effects. Engineers worry about electrostatic patches, thermal drifts, and microscopic roughness, because the force is real but exquisitely small. Visually, the gap between the plates becomes a narrow corridor where only a few standing waves can exist. The outside space looks like a vast sea of modes, and the plates feel a net pressure from that difference. A simple animation can show the allowed wavelengths snapping into discrete patterns between the plates, while outside the spectrum remains continuous and dense. The Casimir force is not proof that universes are born from nothing, and it is not a direct window into cosmic origins. It is proof that the vacuum state is constrained by boundaries and can produce measurable consequences. It tells us that empty space is not merely the absence of matter, but a condition with physical content. It shows that empty is a physical medium with rules, and that changing the rules changes what the vacuum does. In that sense, emptiness behaves less like a blank page and more like an instrument that can be tuned. The plates are not adding new ingredients, they are changing the vacuum's allowed harmonics. Related effects reinforce the same idea, and they come from different corners of physics. Vacuum polarization changes how charges interact at short distances, because the quantum vacuum modifies the effective electric field around a charge. In the field language, the vacuum responds to the presence of a charge by altering the distribution of fluctuations around it. In quantum electrodynamics, the vacuum behaves like a polarizable medium, although the underlying description is field theoretic rather than material. The effective coupling runs with energy scale, and the strength of interactions shifts as you probe closer. The closer you look, the more the vacuum's fluctuations contribute, and the more the measured charge appears to change. The Lamb shift in hydrogen reflects quantum fluctuations modifying energy levels, splitting states that would otherwise be degenerate. It was one of the early triumphs of quantum electrodynamics, because it turned a subtle discrepancy into a precise confirmation. Historically, it helped cement the idea that the vacuum is not a passive backdrop, but an active participant in atomic structure. These are not philosophical claims because they are measured numbers with error bars and apparatus diagrams. They are the kinds of results that forced physicists to take the vacuum seriously, even when the language sounded strange. The vacuum became something you could test, not merely something you could debate. So when physicists say the vacuum can fluctuate, they mean something operational and constrained by equations. The ground state has correlations and uncertainty that affect outcomes, and those outcomes can be predicted and checked. The vacuum is not an anything goes chaos. It is a specific state with a specific mathematical signature. The vacuum is a state in a theory, not a blank page, and that distinction will matter when we return to nothing. The vacuum is nothing only if you define nothing as no particles and no classical objects. That is a legitimate definition inside physics, but it is not the only definition people bring to the conversation. At this point, the documentary's central question sharpens rather than resolves, because the word nothing begins to split into meanings. If the vacuum is something, then universe from nothing cannot mean creation from literal absence. It must mean creation from a particular physical state governed by laws, and that is a narrower, more technical claim. The slogan stays the same, but the content changes once you translate it into physics. In public debates, that translation is often where agreement breaks down, because people think they are arguing about the same word, while they are actually arguing about different reference. Lawrence Krauss made this framing famous, and the public debate often centers on his wording as much as his equations. His thesis is that quantum field theory, plus gravity, can allow a universe to appear spontaneously. In that view, spontaneous means not triggered by a prior classical event, but permitted by quantum rules. In that framing, nothing means no particles, and possibly no classical space, but still a quantum state with laws. The vacuum is not a featureless void, but the lowest energy configuration permitted by the framework. Even the phrase lowest energy carries assumptions, because it presumes a way to define time and dynamics. To understand why this is even thinkable, we need to recall how quantum theory treats causation. Quantum events can occur without a prior trigger in time, as long as they obey probabilistic rules and conservation laws in the appropriate sense. A nucleus can decay without being pushed, and an excited atom can emit a photon at an unpredictable moment. Krauss emphasizes that quantum creation does not require a classical cause in time, the way a match causes a flame. A decay can happen at an unpredictable moment, not because the system is pushed, but because the system has an amplitude to change. The laws do not specify a schedule, they specify probabilities. In the quantum description, the vacuum can be unstable or metastable, and transitions can occur even if a classical picture would forbid them. The key word is amplitude, an allowed possibility weighted by the theory. What matters is not a mechanical shove, but whether the equations assign a non-zero probability to a change. One route is quantum tunneling, where a system crosses a barrier it cannot cross classically. In cosmology, the system might be a small closed universe or a patch of spacetime, described by a wave function over possible geometries. The language is strange because the object is strange, a universe treated as a quantum configuration. In that picture, the barrier is not a hill in ordinary space, but a barrier in configuration space. The amplitude for such a transition can be non-zero even when classical evolution forbids it, and that non-zero number is the opening in the door. The documentary can show a familiar hill, then morph it into an abstract landscape of possible geometries. Visually, the film might show a ball trapped in a valley, then dissolve into a probability cloud that leaks through a ridge. The point is not that the ball tunnels like a ghost, but that the quantum state has support on the other side. The leak is not motion through space, it is weight in the wave function. Another route is vacuum decay, where a false vacuum transitions to a lower energy vacuum through bubble nucleation. A false vacuum is not fake, but a local minimum of an effective potential, stable against small disturbances yet not absolutely stable. The concept is familiar in condensed matter, where phases can persist until a nucleation event triggers a transition. The decay can nucleate a bubble that expands, converting vacuum energy into particles and radiation, as the field rolls toward a lower state. In some models, such a bubble could resemble a big bang from the inside, with a hot, dense beginning. The interior can thermalize, producing a bath of particles as the field's energy is released. The bubble wall becomes a moving boundary between phases, like a front of changing order in a material. Inside, the field configuration is different. and the energy difference can drive rapid expansion and reheating. Visually, the wall can be shown as a thin, luminous shell sweeping outward, separating two kinds of empty. These ideas sound like creation ex nihilo, but the scaffolding is heavy and it is easy to miss what is assumed. They assume quantum laws, a space of possible states, and a rule for assigning probabilities. They also assume that the mathematics describing those states is already in place, which is precisely what critics notice. They also assume something like a vacuum, even if the vacuum is defined in a quantum gravity language rather than on a fixed background. The nothing is not the absence of structure, but a particular structured baseline. The baseline may be minimal, but it is not blank. This is where the scientific debate becomes a debate about definitions and about what counts as an explanation. Critics argue that a quantum vacuum is not nothing in the philosophical sense, because it is a structured entity with fields, symmetries, and dynamical rules. Supporters respond that physics can only speak in physical terms, because its language is measurement and model building. If nothing is defined as the absence of classical objects, then a vacuum qualifies, and the claim becomes meaningful within that definition. But the documentary should make the translation explicit, because otherwise the audience hears a metaphysical claim while the physicist is making a technical one. The disagreement is partly semantic, but it also reveals what each side thinks the origin question demands. Is the goal to explain the emergence of matter and space as we know them, or to explain why there are laws at all? The second demand is deeper, and it is not obviously something physics can satisfy with its current tools. The documentary does not need to pick a winner to make progress, and it should not pretend the dispute is settled. It needs to name the assumptions clearly, and then ask what the assumptions buy us in explanatory power. A mechanism can be brilliant, and still leave the deepest premise untouched. If the vacuum is the starting point, we must ask why that vacuum exists, and why it has the properties it has. That question is not an attack on physics, but a way of locating the edge of physics' current reach. It is also a reminder that starting point is not the same thing as nothing. Historically, the vacuum has been a moving target, and that history matters because it shows how nothing keeps acquiring content. In classical mechanics, empty space was a passive stage, and forces acted across it. Even then, philosophers argued about whether a void could exist, and whether space was a substance or a relation. In the 19th century, fields entered as real entities, and space began to look less empty even before quantum theory arrived. Maxwell's equations made the electromagnetic field a physical presence, capable of carrying energy and momentum through empty regions. The old ether was discarded, but the field remained, an invisible actor with measurable stress and energy flow. Then quantum theory arrived and refused to let the field sit perfectly still, and the vacuum became an active ground state. The shift is not merely conceptual, it is built into the mathematical structure of quantization. The vacuum became the state that minimizes energy, while still respecting commutation relations, and that requirement forces fluctuations. Vacuum energy is the next hinge, because it connects microscopic ground states to cosmic expansion and to the fate of the universe. In general relativity, a uniform energy density acts gravitationally, and it does so in a distinctive way. The stress-energy tensor includes pressure as well as energy density, and the combination determines how spacetime curves. It behaves like a cosmological constant, producing a pressure that can drive accelerated expansion. In the equations, energy density and pressure both contribute to gravity, and negative pressure can make expansion speed up. In plain language, this kind of energy does not merely attract, it can act like a persistent push built into space itself. Visually, the documentary can show a grid of space stretching, with galaxies drifting apart, while a smooth background energy remains unchanged. The key idea is simple in plain language. Some energy does not thin out as space grows. It stays uniform, so as the universe expands, it comes to dominate the budget. In the observed universe, expansion is accelerating, and that is not a subtle effect. Supernova measurements, large-scale structure surveys, and the cosmic microwave background all point to a late-time push that overcomes gravity on vast scales. The evidence is statistical, but it is consistent across independent methods, which is why it is taken seriously. Dark energy is the name we give to whatever causes that acceleration, and the name is deliberately cautious. It admits that we see the effect clearly, even if we do not yet know the underlying mechanism. The camera can show a timeline of cosmic expansion where the curve bends upward, an acceleration that appears late after billions of years. Vacuum energy is an obvious candidate because it is uniform and does not dilute as space expands. A cosmological constant is the simplest model, and it fits the data surprisingly well with only a few parameters. The fit is almost too good, which raises the question of whether we are seeing a deep principle or a lucky simplification. But the match is not straightforward, because quantum field theory seems to predict a vacuum energy that is wildly larger than what the universe displays. The mismatch is so extreme that it becomes a crisis of understanding, not a mere parameter error. It is the kind of discrepancy that suggests we are missing a principle, not a decimal point. This is the cosmological constant problem, sometimes called the vacuum catastrophe, and the word catastrophe is not exaggeration. If we sum zero-point energies up to high frequencies, the result diverges, and the naive value is enormous. Even when we impose cutoffs that seem physically motivated, the remaining value is still absurdly large compared with the observation. Even with reasonable cutoffs, the predicted value overshoots observations by many orders of magnitude, far beyond what scientists tolerate as an unexplained coincidence. The observed dark energy density is tiny on particle physics scales, and yet it dominates the cosmic budget today. That combination, tiny in microphysics, decisive in cosmology, is what makes the problem feel like a signpost to new physics. The tension forces a careful distinction between what vacuum energy means in quantum field theory and what energy means as a source of curvature in general relativity. In the lab, we often care about energy differences, and we can subtract constants without consequence. In gravity, absolute energy density matters, because it curves space-time even if it is uniform. A constant shift in the energy can change the geometry of the entire universe, so the subtraction tricks of ordinary quantum calculations become physically risky. This is one reason the vacuum sits at the fault line between our best theories, quantum field theory and general relativity, because each treats baseline energy differently. So the vacuum is both powerful and problematic, and that duality runs through every universe from nothing story. It can in principle shape the universe's expansion, yet our best theories do not agree on how to compute its gravitational effect. The vacuum is not a settled foundation, it is an interface where our frameworks still grind against each other. This tension matters for universe from nothing arguments, because vacuum energy is often the fuel in the narrative. If vacuum energy is real and gravitating, it could help create or inflate a universe. But if our vacuum energy bookkeeping is deeply wrong, then the origin story built on it is unstable, and the uncertainty shifts from details to foundations. Energy bookkeeping becomes even trickier when gravity is included, because the concept of energy depends on symmetries. In ordinary physics, energy conservation is tied to time translation symmetry, meaning the laws do not change from one moment to the next. In an expanding universe, there is no global time symmetry in the same way, because the geometry itself evolves. That does not mean anything goes, but it does mean that global conservation statements become subtle. General relativity allows local conservation of energy momentum expressed through covariant divergence conditions. In plain language, energy and momentum do not mysteriously vanish at a point, but they can flow and transform as space-time curves. Defining a single total energy for the entire universe is subtle, because it can depend on coordinates and on boundary conditions at infinity. Cosmology often lacks the kind of asymptotic flatness that makes total energy definitions clean. The documentary can visualize this by showing how different coordinate grids slice the same expanding spacetime into different times, changing what a total energy accounting even means. Still, a provocative idea persists in many discussions, because it seems to offer a conceptual escape hatch. The total energy of the universe might be zero, with positive mass energy balanced by negative gravitational potential energy. It is a compelling image, and it echoes older intuitions from Newtonian gravity, where binding energy can be negative. This idea is attractive because it suggests a loophole that sounds almost too neat. If the net energy is zero, then quantum creation might not violate a simple conservation rule, at least in a heuristic picture. A universe could appear as a zero-sum fluctuation, where the cost of matter is paid by the gravitational field's negative contribution. The image is tempting, a cosmic ledger where the grand total remains balanced even as structure appears. Yet the documentary must keep the caveats in view, because the ledger is not universally defined. Gravitational energy is not localized in a coordinate-independent way, and different definitions of energy in general relativity can disagree. Some definitions work well only in special spacetimes, and some rely on symmetries our universe does not exactly possess. So zero total energy is not a settled theorem about our universe, even if it is suggestive in certain models. It is a clue about how creation might be framed, not a proof that it happens, and not a replacement for deeper questions. We now return to quantum fluctuations because they are the mechanism that makes the vacuum feel fertile rather than inert. In quantum theory, fluctuations are not optional noise added by imperfect instruments. They are the minimal uncertainty required by the commutation relations, and they persist even when the system is prepared as carefully as possible. The vacuum is the most orderly state, yet it still contains irreducible spread. A field in its ground state still has a spread of possible values, and that spread can be described as fluctuations in time and space. The vacuum has correlations that can be computed, and those correlations often fall off with distance in characteristic ways. In some contexts, those correlations can be measured indirectly, because they influence how detectors respond and how forces arise. The vacuum is not merely random, because the fluctuations are structured by symmetries and by the field equations. Even when the average field value is zero, the variance is not, and that variance is where the physics lives. When popular accounts say the vacuum borrows energy, they are translating a mathematical statement into a story that fits human intuition. The uncertainty relation between energy and time sets limits on how sharply energy can be defined over short intervals. It does not literally grant permission slips for violating conservation laws, and it is not a loophole that lets nature cheat. In careful language, short-time measurements allow larger energy spreads, and intermediate states contribute to amplitudes. Certain processes can occur with amplitudes that would be suppressed classically, and those amplitudes can add up to measurable effects. The vacuum can contribute intermediate states that influence observable outcomes, even if those intermediate states are not directly seen. So we keep two levels separate, because mixing them produces confusion. The heuristic level uses virtual particles and borrowing energy to build intuition, while the operational level uses correlation functions, loop corrections, and measurable shifts. With that separation, the vacuum becomes a legitimate physical actor, not a mystical placeholder. It can exert forces, shift energy levels, and contribute to effective potentials that shape how fields behave. It can also provide the fluctuations that later become macroscopic structure, which is where cosmology enters the scene. The vacuum is not only a backdrop. In early universe models, it becomes a source of the seeds we later observe. This is where the chapter connects to the previous one's Planck epoch uncertainty. If spacetime itself is quantum, then the vacuum is not just a field state on a fixed background. The vacuum may be a joint state of fields and geometry, meaning the ground state includes fluctuations of spacetime itself. The camera might show a smooth grid dissolving into a foamy, flickering texture, hinting at geometry that cannot settle. In that setting, nothing becomes even harder to define, because even the notion of space is part of what is in question. A vacuum presumes a Hamiltonian and a lowest energy state, but energy depends on how time is defined. And time may be emergent, a derived concept that makes sense only when the universe is already in a semi-classical regime. So the phrase quantum vacuum can hide a deep assumption. It assumes a framework in which a ground state is meaningful. That assumption may be valid in many regimes, yet it becomes delicate when the geometry itself is fluctuating. Quantum cosmology tries to supply that framework, and it offers mathematical proposals for how a universe might be described as a quantum object. Yet it is not yet complete, and different approaches disagree on what the fundamental variables even are. The debate around Krauss often turns on this point, because it marks the boundary between a model and a final explanation. If the laws in the vacuum are assumed, then the origin question is not eliminated. It is relocated, and relocation is not the same as resolution. The documentary can linger here, because it is where the audience feels the difference between a clever mechanism and a complete account. Instead of asking why there is something rather than nothing, we ask why there is a lawful vacuum state at all. Why do fields exist? Why do the equations exist? And why does the space of possibilities have the structure it has? Those questions can sound philosophical, but they also reflect a scientific instinct to push assumptions backward and see what remains. The vacuum story clarifies which assumptions are doing the work and which questions are still unanswered. Physics can sometimes answer why by showing necessity, and that is one of its most powerful moves. It can show that given certain symmetries and consistency requirements, only certain laws work, and many alternatives collapse. Yet that still leaves the meta question of why those requirements hold, and why the universe seems to respect them. The documentary keeps this open, because the field itself keeps it open, and because premature closure would be dishonest. Some physicists treat laws as brute facts, like the rules of the game we find ourselves in. Others suspect deeper principles, symmetry, information, consistency, or mathematical uniqueness that could constrain the space of possible laws. Even those deeper principles, however, invite the same question one level up, and the regress is part of the mystery. The point is not to despair, but to see clearly where explanation currently stops. Yet even without a final answer, the vacuum story does real work, and it changes how we think about emptiness. It shows that emptiness in modern physics is structured, and it shows that the boundary between absence and existence is active. There is also a subtle emotional shift that comes with this realization. The universe begins to look less like a stage where things happen, and more like a set of interlocking constraints that generate what can happen. If that is true, then nothing is not a place you can point to. It is a limit concept, an idea that keeps receding as our theories become more precise. Now we pivot from origin slogans to a mechanism that can be tested indirectly. Inflation theory takes vacuum-like energy and uses it to drive rapid expansion, and it takes quantum fluctuations and stretches them to cosmic scales. In inflation, the universe undergoes accelerated expansion, driven by an effective vacuum energy, often modelled by a slowly evolving field. The key feature is that the expansion is exponential or near exponential for a brief early period. That rapid stretching smooths and flattens the observable universe, while also magnifying tiny quantum fluctuations. What begins as microscopic uncertainty becomes, after expansion, a pattern spread across billions of light years. Tiny quantum fluctuations in the inflating field become density perturbations, because different regions end inflation with slightly different conditions. Those perturbations later seed galaxies and leave patterns in the cosmic microwave background. The CMB is a nearly uniform glow, but it is not perfectly uniform, and the deviations are the story. The mottled map, hotter and colder patches by tens of microkelvin, becomes a fossil of vacuum noise amplified into a cosmic blueprint. Visually, the documentary can dissolve from a jittering quantum field to a swelling sphere, then to a CMB sky map, and finally to the filamentary web of galaxies. The same pattern, translated across scales, becomes an argument you can almost see. This is the crucial bridge for the documentary's momentum because it connects the vacuum to evidence. The vacuum is not only a philosophical battleground about the meaning of nothing, it is a candidate engine for early universe dynamics, and its fingerprints may be written into the statistical properties of the CMB. The question becomes less like a slogan and more like an inference chain. If inflation happened, then quantum fluctuations are not just microscopic curiosities confined to particle physics. They become the origin of large-scale structure, shaping where matter later collects and where voids open. The universe we see, clusters, filaments, and vast dark gaps, could be the grown-up version of the vacuum's smallest uncertainties. That thought is both unsettling and elegant, because it makes the everyday sky a monument to quantum rules. It also invites a quiet question. When we look at the largest structures in nature, are we seeing the amplified trace of the smallest permissible jitter? So Chapter 4 ends with a sharpened mystery and a clearer map of assumptions, rather than a final verdict. Nothing in physics often means a vacuum state with fields and laws, and that vacuum can fluctuate, exert forces, and possibly drive expansion. But if the vacuum is already something, then the deepest question remains, and it remains in a more precise form. Why do the vacuum and the laws exist at all, and why does the universe permit this particular kind of structured emptiness? The next chapter turns to inflation as the mechanism that makes quantum seeds grow into a universe we can observe. And as we move forward, we carry the central tension with us, between the power of our models and the mystery of their starting point. We have a vacuum that is not empty, and a Planck frontier where time wobbles under quantum uncertainty. Now we ask how that restless baseline becomes the ordered sky we measure, with temperatures, angles, and patterns that repeat across billions of light years. The transition is not just poetic, it is a calculation, because the sky's smoothness can be expressed in numbers. On screen, the universe looks calm at first glance, an almost uniform glow in microwave light. Yet the physics beneath it is anything but calm. The glow is the cosmic microwave background, a relic radiation field that has been cooling for 13.8 billion years. The question is not whether the early universe was hot, because the evidence for that is overwhelming. The question is how a hot beginning became so smooth, so geometrically balanced, and yet still laced with the tiny irregularities that later formed everything. Inflation enters as a mechanism that turns mystery into dynamics. It proposes a brief early era when expansion accelerated, driven by vacuum-like energy that behaved almost like a temporary cosmological constant, instead of assuming the universe simply began in an improbably special state. Inflation tries to show how a broad range of beginnings can be pushed toward the same observable outcome. It is an attempt to replace improbable initial symmetry with a process that manufactures symmetry. The central question tightens as we move from description to cause. If the universe can grow from quantum structure, what set the conditions for that structure to inflate, rather than fragmenting, collapsing, or remaining trapped in a different phase? Even in the simplest models, the onset of inflation is a dynamical threshold, not a guaranteed default. In other words, inflation must start, and a start is a physical event. Start with the puzzles that the hot Big Bang alone does not naturally solve, even though it explains nucleosynthesis, expansion, and the existence of the cosmic microwave background. These are not philosophical gaps, but quantitative tensions that appear when we extrapolate the simplest equations backward in time. The standard model of cosmology works beautifully after the first fractions of a second, yet it seems to inherit delicate coincidences from earlier moments. First is the horizon problem, written across the cosmic microwave background like a signature. Regions far apart look almost identical, even though light could not have connected them in the available time. When we look left and right across the sky, we are comparing places that, in a basic Big Bang timeline, never had a chance to communicate. The problem is causal, and in relativity, causality is geometry. In the standard picture, opposite sides of the observable sky were never in causal contact before recombination, when atoms first formed and photons began to travel freely. Before that moment, the universe was an opaque plasma, and photons scattered constantly off free electrons. Yet the CMB temperature varies only by parts in 100,000, a precision that suggests a shared thermal history. It is as if two distant rooms match temperatures to within a fraction of a degree, despite never exchanging air. Uniformity is not perfect, and the imperfections matter because they become the seeds of structure. But the baseline sameness is still too strong to be accidental in a naive picture, especially when the uniformity extends across angular scales larger than the causal horizon at that time. A causal horizon is not a wall, but it is a limit on coordination, like the maximum distance a message could travel. The map looks like a single system, not a patchwork of disconnected regions. Second is the flatness problem, hidden in the geometry rather than the temperature. The universe today appears close to spatially flat, meaning the large-scale curvature is near zero within observational uncertainty. In everyday terms, the cosmos behaves as if Euclidean rules almost apply on the biggest scales we can test. That near flatness is encoded in the density parameter, omega, which observations place extremely close to 1. In the Friedmann equations, curvature grows in importance when you run the clock backward, unless it was tuned extremely close to critical early on. A tiny deviation from flatness in the early universe would amplify dramatically over time, the way a slight imbalance compounds in a long calculation. In numerical terms, the required early tuning can be astonishingly tight, depending on how far back you extrapolate. The early universe seems balanced on a knife edge, with the critical density tracked to extraordinary precision. Third is the relic problem, where certain particles should exist but do not appear. Grand unified theories predict heavy relics like magnetic monopoles that should survive once produced, because they are stable and difficult to annihilate away. In many models, phase transitions in the early universe naturally create such defects, much as cooling water can form cracks in ice. The analogy is more than visual, because it is about domains choosing different states as symmetry breaks. If the early universe reached those energies, monopoles should be abundant today, and their magnetic charge would make them conspicuous. Observations show none, which forces either new physics that prevents their production or a dilution mechanism that makes them vanishingly rare. The problem is not merely aesthetic, because even a small relic abundance could overclose the universe or disrupt later evolution. A universe clogged with relic mass would expand and cluster in ways we do not see. Inflation claims to solve all three with one move, and the move is geometric. It stretches space so quickly that initial patches become enormous, smoothing and diluting as they expand. The same mechanism that expands distances also pushes curvature toward flatness and spreads unwanted relics so thin that they effectively disappear. It is a single episode with multiple observable consequences, which is why it is taken seriously. Define the core idea with minimal assumptions, because the power of inflation comes from a simple ingredient. A field sits in a high-energy state with nearly constant energy density for a short time, long enough to dominate the cosmic budget. This field is often called the inflaton, though the name is a placeholder for whatever microphysics does the job. In the mathematics, it behaves like a scalar field with a potential energy landscape. That energy behaves like a vacuum term in general relativity, and its gravitational effect depends on both density and pressure. It has negative pressure, which changes gravity from decelerating expansion to accelerating expansion, a counterintuitive result that is nevertheless built into Einstein's equations. In cosmology, pressure gravitates, and negative pressure can act like repulsion on large scales. The sign of the pressure matters because it enters the acceleration equation directly. The intuition is equation of state behavior, a compact way to describe how a component responds to expansion. For ordinary matter, pressure is small and density dilutes with expansion because particles spread out as volume grows. For radiation, pressure is positive and density dilutes even faster because photon wavelengths stretch and their energies drop. Those scalings are simple. Matter falls like 1 over volume, while radiation falls even faster because of redshift. For vacuum-like energy, pressure is negative and density stays almost constant, even as the universe expands. That constant density is crucial because it means the expansion does not drain the source driving it. The field behaves like a reservoir that does not thin out in the usual way. In slow-roll inflation, the field changes so gradually that potential energy dominates over kinetic energy. When density stays constant while volume grows, total energy in that component effectively increases with expansion, which sounds like a paradox. In general relativity, this is not a violation of local conservation, because energy conservation is subtle in an expanding spacetime. The bookkeeping is handled by the stress-energy tensor and the geometry together, not by a global energy ledger. The expansion does work on the universe, and the concept of total energy depends on how you slice spacetime. The expansion is not objects flying through space like shrapnel from an explosion. It is the metric itself stretching, so distances between co-moving points grow as the scale factor grows. Galaxies can remain nearly at rest in their local frames while the space between them increases. This is why expansion can coexist with local stability, from atoms to solar systems. That's why inflation can be faster than light without breaking relativity, a point that often confuses first encounters with the idea. Relativity limits motion through space-time, not the growth of space-time itself. During inflation, two distant points can separate faster than light because no signal is locally outrunning a light beam. The light cones remain intact, even as the grid they sit on is being stretched. During inflation, the scale factor can grow nearly exponentially, multiplying by enormous factors in a tiny fraction of a second. A region smaller than an atom can, in principle, become larger than the observable universe, depending on the duration and energy scale. Visualize a tiny speck on the screen, then watch it balloon until it fills the frame, while its internal texture becomes smoother. The numbers are extreme, but the mathematics is the same mathematics we use for gentler expansion today. Now return to the horizon problem with this new tool, and watch what changes in the causal diagram. Before inflation, the region that becomes our observable universe was small enough to equilibrate, exchanging particles and radiation until it reached a common temperature. In that compressed state, causal contact is easy, because distances are tiny and interactions are rapid. The universe had time to mix in the same practical sense that a hot gas mixes in a small container. Inflation then stretches that equilibrated patch beyond the horizon, like pulling a small, uniform piece of fabric until it covers a vast area. The CMB looks uniform because it comes from a once-connected region, even though it later appears disconnected in the standard Big Bang timeline. The uniformity is not a coincidence, but a fossil of an earlier, smaller universe. On screen, horizon circles that once overlapped shrink relative to the stretched patch, leaving apparent islands that were once neighbours. Return to flatness with the same tool, because geometry responds sharply to accelerated expansion. Rapid expansion drives curvature towards zero, the way a small patch of a sphere looks flatter when magnified. If you zoom in far enough on Earth's surface, it looks like a plane, even though the globe is curved. Inflation is like an enormous zoom-in, applied to space-time itself. In the equations, the curvature term becomes negligible, compared with the vacuum-like energy term during accelerated expansion. Near-critical geometry becomes an attractor, meaning many initial conditions evolve toward the same outcome. The knife edge becomes less precarious, because the dynamics steer the universe toward flatness. What looked like fine-tuning becomes, at least partly, a consequence of the expansion history. Return to relics with the same tool, and the logic is almost brutally simple. Any pre-existing heavy particles are diluted by the enormous increase in volume, so their number density plummets. Monopoles, if produced before inflation, become so rare that none remain in our observable region. Even one per galaxy becomes one per unimaginable volume, effectively zero for us. Inflation does not forbid them, and it does not disprove the theories that predict them. It hides them by making our patch too small a sample to contain even one given the dilution. In that sense, inflation turns a potential contradiction into an observational absence. It is a solution by stretching, not by rewriting particle physics. This is the first narrative lift, and it is why inflation became influential so quickly. A single early episode can explain several otherwise unrelated facts about the present universe, tying temperature uniformity, geometric balance, and particle relics into one coherent story. It is a unification of puzzles, not by adding separate fixes, but by changing the early expansion history. The elegance is real, and so is the temptation to treat elegance as proof. Historically, this was not a slow drift of ideas, but a rapid response to concrete problems. In the early 1980s, cosmologists were wrestling with the horizon and flatness issues in increasingly quantitative ways. Alan Guth's original proposal, and the later refinements by Linde and by Albrecht and Steinhardt, turned a qualitative idea into a workable framework. The proposal that an early accelerated phase could solve them reshaped the field, because it offered testable consequences rather than mere philosophical comfort. But inflation is not only a smoothing machine, it is also a generator of structure, because quantum fluctuations cannot be turned off, even in a vacuum-like state. The very mechanism that erases large irregularities also amplifies tiny ones, leaving behind a delicate pattern that later becomes visible in the sky. In a sense, inflation is both eraser and pen, first wiping the slate, then writing in faint ink. Here the documentary reconnects to the vacuum chapter, because the same ground state jitter that shifts atomic levels can be stretched into cosmic patterns. In quantum field theory, a field cannot sit perfectly still, because the uncertainty principle enforces residual fluctuations. Even empty space carries fluctuating modes, and inflation gives those modes room to grow. What begins as microscopic noise becomes, after stretching, a blueprint for cosmic structure. Quantum fluctuations occur in the inflaton field and in the metric itself, because spacetime participates in the dynamics. Inflation takes those microscopic variations and freezes them into classical-looking perturbations, the kind that can be treated statistically as real density differences. The transition is subtle, but the outcome is robust, a spectrum of ripples imprinted on the universe. The ripples are not objects, but variations in curvature and energy density that guide later motion. The key step is horizon crossing during inflation, and the phrase has a precise meaning. A fluctuation starts smaller than the Hubble radius, behaving like an ordinary quantum mode that oscillates and can be influenced by local physics. In that regime, interactions can smooth it out, and causality can keep it in check. Think of it as a wave that fits inside the region, where physics can coordinate its phase. As space expands, its wavelength is stretched until it exceeds the Hubble radius, the scale beyond which regions cannot communicate within a Hubble time. At that point, causal microphysics cannot erase it. because the mode is effectively outside the domain where local processes can coordinate. The oscillation slows, and the amplitude becomes nearly constant. The wave is still there, but it is no longer ringing in the usual way. The fluctuation becomes effectively frozen as a curvature perturbation, a small change in the local expansion history. Later, when the Hubble radius grows again after inflation ends, the mode re-enters and influences matter and radiation. What was once a quantum wiggle becomes a classical initial condition for cosmic evolution. The universe carries those initial conditions forward, like a memory encoded in geometry. This is how inflation turns quantum uncertainty into a map, and the map is written in statistical language. Slight differences in density become the seeds that gravity later amplifies into galaxies, clusters, and the filamentary cosmic web. Without those seeds, matter would remain too uniform to form the structures we see. On screen, faint ripples in a translucent early universe gradually sharpen into a network of bright nodes and dark voids. The predicted pattern is statistical, not deterministic, and that distinction matters for interpretation. Inflation does not predict where a particular galaxy will form, because the fluctuations are random draws from a probability distribution. But it predicts the distribution of initial ripples, including how their amplitudes depend on scale. It predicts a kind of cosmic texture, not a specific cosmic photograph. The simplest models produce a nearly scale-invariant spectrum, which means fluctuations have almost the same power on many length scales. In practice, nearly carries information, because small deviations encode the shape of the inflaton potential and the rate at which the field rolls. A perfectly scale-invariant spectrum would be a special limit, and nature seems to prefer a slight tilt. That tilt is small, yet it is measurable, which is part of the triumph of modern cosmology. They also predict near-Gaussian statistics to first approximation, meaning the fluctuations behave like a random field, with correlations set by a small set of parameters. Gaussianity is the hallmark of simple quantum fluctuations in a weakly interacting regime. Non-Gaussian features, if detected, would point to more complex dynamics, such as strong interactions or multiple fields. The search for non-Gaussianity is therefore a search for hidden complexity in the earliest moments. Now connect to the CMB, our best fossil of early conditions, because it is a snapshot of the universe at about 380,000 years. The temperature anisotropies trace density and gravitational potential variations at last scattering, when photons decoupled from matter. What we see as hot and cold spots are not simply temperature differences, but a mixture of gravitational redshift, Doppler motion, and intrinsic density contrasts. The sky is a layered signal, and extracting it requires careful modelling. On a full sky map, the CMB looks like a soft, mottled sphere. Blue and red speckles spread across a nearly uniform background. The average temperature is about 2.7 Kelvin, and the variations are tens of microkelvin, a whisper on top of a roar. Yet those microkelvin differences are enough to reconstruct the early power spectrum with exquisite precision. The camera can linger on the map, then slowly zoom into the speckle pattern until it feels like terrain. Inflation predicts the phases of acoustic peaks should be coherent, because the perturbations start with a specific pattern of initial conditions. Before recombination, photons and baryons behave like a coupled fluid, and gravity drives oscillations that leave peaks in the angular power spectrum. The peaks seen by WMAP and Planck match that coherence, supporting an inflation-like origin. Those peaks are not decorative, because each one encodes a physical scale, like a ruler laid across the early plasma. The measured scalar spectral index is close to, but not exactly 1, and that not exactly is a clue. A value slightly below 1 fits slow-roll inflation, where the field changes gradually and the expansion is almost but not perfectly exponential. The tilt is a quantitative fingerprint, linking observation to the shape of the potential. It suggests that inflation was not a perfectly steady state, but a slowly evolving process. Non-Gaussianity is constrained to be small, which is a triumph of the simplest inflationary expectations. That rules out many exotic models, though it does not uniquely select one inflaton potential. The data favour the mechanism, not a single microphysical story, and that is both reassuring and frustrating. The universe seems to be telling us the broad outline while withholding the fine print, so inflation is supported in broad strokes, but not pinned down in detail, and the distinction is important for scientific caution. We have strong evidence for a particular kind of initial perturbation spectrum, and inflation is the leading framework that produces it naturally. but the identity of the inflaton, the exact potential, and the deeper embedding in particle physics remain open. The theory is compelling, yet its microscopic foundation is still under construction. The next observational target is primordial gravitational waves, because inflation generically produces tensor fluctuations, ripples in spacetime itself. These are not waves from merging black holes, but a background generated by quantum fluctuations of the metric during inflation. Their amplitude depends on the energy scale of inflation, making them a direct probe of physics far beyond accelerators. If detected, they would be a rare message from energies we cannot reproduce on Earth. Those tensors would imprint a distinct pattern in CMB polarization, called B modes, a swirling signature that cannot be produced by simple density perturbations alone. Polarization arises because photons scatter off electrons, and the local quadrupole anisotropy imprints a preferred direction. Tensor modes twist that pattern into curls, leaving a subtle rotational component. On screen, straight polarization ticks curl into faint spirals, then fade into the noise floor. Detecting them would measure the energy scale of inflation, turning a speculative epoch into a quantified one. It would also help distinguish among families of models, because different potentials predict different tensor-to-scalar ratios. In that sense, B modes are not just another data point, but a lever that could move the whole theory. A single number could eliminate entire classes of models. So far, B mode searches have produced upper limits and cautionary lessons, reminding us how hard precision cosmology can be. Foregrounds like galactic dust can mimic the signal and must be subtracted with multi-frequency observations. The sky is not a clean laboratory, and our own galaxy is a bright contaminant. Even the instruments themselves must be calibrated against subtle systematics, because the signal is so small. The absence of a detection does not kill inflation, because many viable models predict tensors too small to see with current instruments. It narrows the space of models, pushing toward lower tensor amplitudes or different dynamics that suppress gravitational waves. Constraints are still progress, because they prune the theoretical landscape. In science, not seeing something can still be a measurement if you know how sensitive your search was. At this point, the chapter shifts from what inflation does to how it ends, because a universe dominated by vacuum-like energy must transition into a hot plasma. Inflation cannot be the whole story, since our universe contains particles, radiation, and the thermal history required for nucleosynthesis. The graceful exit is not optional, and it must connect to the hot Big Bang evidence. The story must hand off smoothly from accelerated expansion to the familiar cooling universe. That transition is reheating, and it is where inflation connects back to the familiar successes of early universe physics. The inflaton's energy must become particles, populating the universe with the ingredients for later chemistry and structure. In many models, inflation ends when the field rolls down its potential, and the vacuum-like state is no longer sustained. The negative pressure relaxes, and the expansion returns to a decelerating, radiation-dominated regime. In many models, the field begins to oscillate around the minimum of its potential, behaving like a coherent condensate. Those oscillations can decay into other fields, producing matter and radiation through couplings that depend on the underlying particle physics. The details matter because they set the reheating temperature and influence what species are produced. A higher reheating temperature can open pathways to heavier particles, while a lower one can close them. Reheating is not a single event in all models, and the phrase can hide complex dynamics. It can be a period with parametric resonance and rapid particle production, sometimes called preheating, where energy transfer is explosive rather than gradual. Fields can amplify each other, and particle numbers can grow non-thermally before settling into equilibrium. On screen, the smooth infleton background fractures into a storm of excitations, then thermalizes into a glowing plasma. The essential point is conversion, and the conversion is physical rather than metaphoric. Vacuum-like energy becomes a thermal bath, setting the initial conditions for nucleosynthesis and the later CMB. Once the universe is filled with radiation again, the standard hot Big Bang evolution resumes, now with initial conditions shaped by inflation. The success of nucleosynthesis then becomes a consistency check, because it requires the universe to be hot and dense at the right time. This is where the phrase creation reappears with technical meaning, and the meaning is precise. Particles are produced from field energy, not from a literal void, through processes allowed by quantum field theory in a time-dependent background. The universe does not conjure matter from nothing. It transforms energy stored in a field into excitations we call particles. The nothing of popular language is in physics a structured state with rules. Inflation therefore reframes the origin story, and it does so without claiming to answer every metaphysical question. It does not start from nothing in the philosophical sense, but from a state with a field and a potential, plus the laws that govern them. The narrative becomes more mechanistic, but the deepest why is not erased. We can model the engine, yet still wonder who built the engine room. Now the tension rises because the mechanism is powerful enough to create new puzzles, especially when we follow it beyond our observable patch. Some inflationary models do not end everywhere at once, because quantum fluctuations can kick the field back up its potential in some regions. The end of inflation can be local, while the global process continues. The same randomness that seeds galaxies can also keep inflation alive elsewhere. Eternal inflation is the idea that inflation can be self-reproducing, a kind of stochastic growth driven by quantum noise. Quantum fluctuations can keep some regions inflating even as others exit, because the field's value performs a random walk on top of its classical motion. In a large enough inflating volume, rare upward fluctuations can dominate the future volume. The result is a process that never finishes, even though it ends in many places. In such models, inflation ends locally in pockets, and each pocket becomes a hot Big Bang region with its own reheating surface. Meanwhile, the larger spacetime keeps inflating, creating more volume in which more pockets can form. The picture is not a single explosion, but a branching process. On screen, the inflating background darkens and expands, while bright bubbles bloom like sparks in slow motion. Those pockets are often called bubble universes, and the term is meant to evoke a visual geometry. Imagine an inflating background like a dark, expanding ocean, with bright bubbles nucleating and growing where inflation ends. Each bubble contains a region that looks, from the inside, like an entire universe. The bubble wall is not a physical boundary you could reach, because the geometry itself keeps it out of causal contact. The term multiverse then means an ensemble of causally disconnected regions produced by the same underlying process. It does not necessarily mean different laws of physics, though some models allow different low-energy outcomes through symmetry breaking. The key point is causal separation, because the inflating background stretches space so fast that bubbles cannot easily communicate. The multiverse, in this technical sense, is a consequence of dynamics, not a fantasy of parallel worlds. Define the multiverse carefully to avoid overclaiming, because the word carries cultural baggage. It is a theoretical consequence of certain models, not an established observational fact. The documentary can acknowledge it as an implication, while keeping the epistemic boundary clear. The difference between suggested by equations and confirmed by data is the difference between speculation and science. The multiverse changes what an origin means, because it reframes our observable universe as one region among many. If inflation is eternal to the future, then our observable universe is not the whole story, but a local patch with a finite past within a much larger space-time. The beginning becomes a question about the inflating background, not just our bubble. It invites a strange thought. Our cosmic history may be typical only within our local domain. It also changes what a beginning means in time, because global time in such spacetimes can be difficult to define. Some versions still require an initial inflating state, while others suggest no global end and an unclear global start. Even the language of before and after can become coordinate dependent. When time is tied to expansion, and expansion is patchy, the usual intuition can fail. This pushes the documentary back to the central question, because explanatory success creates a new demand. If inflation explains our patch, what explains inflation's initial conditions, and why did the inflating state exist at all? The mechanism is a bridge, but we still want to know what anchored the far end. A bridge is useful, yet it does not tell you why the two shores were there. Why did the inflaton start high on its potential, if such a field exists, rather than already near its minimum? Why was the region smooth enough to begin inflating rather than collapsing into a chaotic mix of gradients and curvature? These are not rhetorical flourishes, because the onset of inflation can require conditions that are themselves special. In some models, too much inhomogeneity can prevent inflation from ever taking hold. Inflation can dilute initial irregularities, but it may not erase the need for a special starting patch, depending on the model. The mechanism shifts the burden rather than removing it, moving fine-tuning questions from late-time geometry to early-time field configuration. In some scenarios, the required patch can be small, but it must still exist. The mystery becomes more focused, not necessarily smaller. There is also a measure problem in eternal inflation, and it is more than a technical footnote. If infinitely many bubbles form, probabilities become ambiguous without a rule for counting, because ratios of infinities are not automatically meaningful. Different measures can yield different predictions for what typical observers should see. The challenge is to define typical without smuggling in the answer. The theory risks becoming flexible enough to fit almost anything, which is dangerous for scientific testability. If every outcome occurs somewhere, then the challenge becomes explaining why we observe this particular outcome rather than another. The measure problem is an attempt to restore predictive power, but it highlights how subtle the framework can be. It also raises a quiet question. What does it mean to test a theory that describes regions we can never access? This is the narrative peak of the chapter, where success and uncertainty sit side by side. Inflation can explain the uniform sky and the seeds of structure, yet it threatens to make origins harder to define. It is a theory that clarifies the middle of the story while complicating the first page. The same exponential expansion that smooths our patch also hides what came before. The documentary holds both truths at once, because that is what the evidence and the mathematics suggest. Inflation is our best developed bridge from quantum fluctuations to galaxies, and it is also a doorway to deeper uncertainty about beginnings. The sky becomes both confirmation and concealment, an archive that preserves early physics while erasing earlier chapters. We can read the ink, yet the paper's origin remains unknown. Now we pivot toward what comes next in the series, because the unresolved questions point beyond classical cosmology. If inflation needs initial conditions, we must ask whether those conditions come from quantum cosmology, where spacetime itself is subject to quantum rules. The origin problem becomes a problem about the origin of the stage, not just the actors. We are forced to ask whether geometry can be quantized in a way that makes beginning a calculable concept. The earlier problem of time returns in a new form, and it becomes more than a philosophical aside. If time emerges, then the phrase before inflation may be ill-defined in the deepest regime, because before presumes a time parameter that may not exist. Our narrative instincts can outrun the formalism. The universe may not have begun in time, but with time. We also return to the strict meaning of nothing, because the word is often used loosely. An inflating state is not nothing, because it presumes fields, laws, and a spacetime description, even if that spacetime is rapidly changing. Inflation can explain how a particular state evolves, but it does not eliminate the need for a state. The question becomes sharper: what selects that state, and what makes it possible? So the next chapters widen the search, following the questions inflation leaves behind. They examine pre-Big Bang scenarios, bounces, no-boundary proposals, and other quantum origin frameworks, each trying to make sense of initial conditions without smuggling them in by assumption. The aim is not to replace inflation, but to understand what could set it up. Inflation remains a central chapter, yet it may not be the first chapter. The transition is clear and unsettling, because it preserves the mystery while sharpening the logic. Inflation may be the engine of our observable universe, but the ignition key remains hidden. We can describe the acceleration, the fluctuations, and the reheating, yet still not know why the process began. The deeper we understand the mechanism, the more precisely we can state what we do not know. We end with the question sharpened rather than closed, because that is where the frontier lies. If a whisper of quantum noise became the cosmic web, what chose the stage on which inflation began, and what fixed the rules the noise had to follow? The sky's a record, but it is not the whole archive. And if that stage is already something, fields, potentials, and a space-time framework, then the mystery of nothing has only changed its address, not its power. The Big Bang in modern cosmology is not a first spark in emptiness, and it is not a firework exploding into pre-existing space. It is the hot, dense phase our evidence reconstructs with confidence, using light, nuclei, and the faint afterglow that still fills the sky. When cosmologists say Big Bang, they usually mean a thermal history, a universe once hot enough that atoms could not exist, hot enough that even protons and neutrons were still negotiating their identities, On screen, that history is often drawn as a narrowing funnel or a shrinking line, but the real story is written in spectra. The cosmic microwave background, cooled to 2.7 Kelvin today, is a photograph of a plasma that once glowed at roughly 3000 Kelvin. The abundance of helium and deuterium is a fossil record of nuclear reactions that ran for minutes, not eons, when the universe was dense enough to fuse light elements efficiently. When we ask what happened before the Big Bang, we are already smuggling in time, as if time were a container the universe sits inside. The word before assumes a timeline that may not extend past space-time's own emergence, and that assumption is precisely what is under dispute. The question sounds simple, yet it hides a technical demand. Define time in a regime where our best theories are not yet unified. So Chapter 6 begins with a disciplined reset of language, because in cosmology, sloppy words can quietly create impossible problems. Pre-Big Bang can mean earlier than the hot phase, meaning earlier than nuclear synthesis and recombination. Or it can mean deeper than classical time, meaning beyond the point where space-time itself is a reliable concept. These are not the same question, and the difference matters. If time is fundamental and stretches through the Planck regime, then before might be meaningful even if it is inaccessible to direct observation. If time is emergent, then before becomes a category error, like asking what is north of the North Pole. In that second case, the right question is not what happened earlier, but what structure replaces earlier. This is where the problem of time returns from quantum gravity, no longer abstract but unavoidable. In Wheeler-DeWitt-style approaches, the universe can be described without an external clock, because there is no outside vantage point to supply one. The formalism compresses dynamics into a constraint, and the wave function is not labelled by a universal time parameter. That feels alien because everyday physics is built around time evolution. A timeless equation can still contain change as correlations between variables. The way a map can encode routes without moving, time becomes relational, read off from internal degrees of freedom, such as the value of a field that can serve as a physical clock. In plain terms, one part of the universe can function as a wristwatch for another part. The tick is not imposed from outside, it is extracted from within. That shift is not philosophical decoration because it changes what an origin event even means. An event presumes a time parameter, and a time parameter presumes a background structure that may not exist at the deepest level. If the universe is a closed system, then the usual separation between laws and initial time becomes less clean. The beginning becomes a boundary in configuration space, not a moment on a calendar. Now we confront the phrase that keeps returning in public science, before the Big Bang. In the standard hot Big Bang model, the scale factor shrinks towards zero in the past, and densities rise as we rewind the expansion. Classical general relativity then predicts a singularity under broad conditions, and the mathematics becomes harshly decisive. The Penrose, Hawking singularity theorems developed in the 1960s and early 1970s show that if certain energy conditions hold, and the universe is expanding today, then geodesics cannot be extended indefinitely into the past. The result is not a cartoon of infinite stuff, but a statement about the limits of classical space-time. Singularity theorems are not a proof of infinite density as a physical object, as if nature literally builds an infinity you could touch. They are a proof that classical space-time geodesics cannot be extended, meaning the theory's own notion of before runs out. A geodesic is the path a freely falling particle follows, and incompleteness means there are paths that simply stop, with no further classical description. That is why singularities are often treated as warnings, not destinations. So the singularity is a signpost that our description fails, and it points toward a missing ingredient. The natural suspect is quantum gravity, where geometry and matter cannot be separated cleanly, and where the smooth fabric of space-time may be replaced by something discrete or fluctuating. Near the Planck scale, around 1035 meters and 1019 giga, electron volts, quantum uncertainty is expected to infect geometry itself. The very idea of a sharply defined distance becomes questionable. One response is to replace the singularity with a bounce, a word that sounds simple but carries heavy technical baggage. The universe contracts, reaches an extreme density, then rebounds into expansion, turning the Big Bang into a turning point rather than an absolute start. Visually, the timeline stops looking like a line that ends and starts looking like a curve with a minimum. The beginning becomes a bridge. A bounce is not one model, but a family of ideas, ranging from effective modifications of Einstein's equations to fully quantum descriptions. The common claim is that new physics prevents the scale factor from reaching zero, so that volume never vanishes and curvature never diverges. In some versions, the bounce is symmetric, like a mirror reflection of contraction into expansion. In others, it is asymmetric, with different physics on either side. The appeal is immediate and dramatic because it answers a psychological pressure as well as a scientific one. A bounce makes the hot Big Bang a transition, not an absolute beginning, and it invites a deeper history behind the visible universe. It also offers a way to talk about before without pretending we have a complete quantum gravity theory. Yet that invitation comes with strict requirements. A bounce must do more than avoid infinity, because avoiding infinity is only the first checkpoint. It must reproduce the observed smoothness, the near-flat geometry, and the measured spectrum of primordial perturbations. Those perturbations are not optional details. They are the seeds of galaxies and clusters, and they are mapped with exquisite precision in the microwave background. Any alternative to a simple singular start must explain why the sky looks the way it does. In a contracting phase, horizons behave differently than in an expansion, and causal structure can be reshuffled in surprising ways. That can help causal contact, because regions that appear disconnected in an expanding picture might have interacted during contraction. But contraction can also amplify anisotropies and inhomogeneities, turning small irregularities into dominant features. The universe can become lopsided, wrinkled, and unstable if the wrong terms take over. The central technical challenge is stability, and the phrase hides a specific danger. Generic contraction in general relativity tends to make shear and curvature dominate, producing a chaotic mixmaster approach, where different directions expand and contract at different rates. This behavior was studied in the Blinsky-Kalatnikov-Lifshitz picture, which suggests that near a classical singularity, the dynamics can become violently anisotropic. In that regime, a smooth bounce is not automatic, so successful bounce scenarios need a smoothing mechanism, not just a mechanism that halts collapse. They must suppress anisotropy growth and keep the contraction from fragmenting into a patchwork of regions with different fates. Some models use special forms of matter with unusual equations of state, while others rely on quantum corrections that effectively damp the dangerous modes. Either way, the bounce is a choreography, not a single step. Another challenge is entropy, the quiet accountant of cosmic history. If the universe cycles through many bounces, entropy tends to accumulate, making later cycles larger and longer, because entropy is hard to erase. Heat spreads, structures form and decay, and the number of accessible microstates grows. A truly periodic universe would need a way to avoid this thermodynamic ratchet. That entropy build-up threatens cyclic repetition, and it forces a choice. Either cycles cannot be truly identical, with each cycle stretching the next, or some mechanism must dilute or reset entropy. Some proposals imagine that expansion can be so vast that entropy density becomes negligible, even if total entropy grows. Others suggest that what we call a cycle might involve only a patch, not the whole of reality. Even for a single bounce, entropy matters, because the arrow of time is tied to entropy increase. A bounce forces us to ask how the arrow passes through, and whether it is continuous or bifurcated. We are used to time pointing one way, from lower entropy to higher entropy, but a bounce introduces a minimum of volume that tempts the imagination. Does the arrow care about volume, or only about microstates? Does entropy keep increasing through the bounce, making the bounce a minimum of volume, but not a reversal of time's direction? Or does the arrow flip, creating two time directions away from the bounce, like a valley where time flows outward on both sides? These are not merely interpretive choices, because they determine what counts as initial. If the arrow flips, the bounce is not a beginning but a midpoint. These questions also touch the meaning of memory and records, because records are physical correlations that typically require entropy production. If observers existed on both sides, would they remember the bounce, or would the conditions erase traces? A bounce that is thermodynamically gentle might preserve correlations, while a violent bounce could scramble them. The arrow of time is not just a metaphor, it is an accounting of information. Now we pivot from classical bounces to quantum gravity-inspired bounces. The key idea is simple, even when the mathematics is not, and it can be stated without committing to a single theory. At extreme densities, quantum effects can modify gravity's effective behavior, and those modifications can act like repulsion in regimes where classical gravity would only attract. In plain language, spacetime can push back when compressed too far. One can describe this without endorsing a single framework, because the motif appears across approaches. Many approaches suggest that the classical energy conditions can fail in quantum regimes, which weakens the assumptions behind singularity theorems. In quantum field theory, negative energy densities can appear in constrained ways, and vacuum fluctuations can violate classical intuitions. The details are delicate, but the door is open. In effective equations, new terms appear at high curvature, often suppressed at low curvature, and dominant only near the Planck regime. Those terms can cap density and turn contraction into expansion, producing a bounce as a consequence of modified dynamics. The bounce is then not a miraculous exception, but a predictable outcome once certain thresholds are crossed. The universe becomes a system with built-in regulators. The bounce then becomes a quantum transition in geometry, and the word transition is doing real work. Spacetime remains, but its classical description breaks and re-emerges, like a material that changes phase under pressure. We can picture a smooth metric giving way to a quantum foam, then condensing again into a classical geometry. The visual is not literal, but it captures the sense of a regime change. This is where earlier chapters' caution applies, because it is easy to smuggle metaphysics into equations. A quantum bounce still assumes laws, degrees of freedom, and a rule for evolution or amplitudes, even if the rule is expressed as a constraint rather than time evolution. It does not create the universe from philosophical nothing, because the mathematical structure is already there. It changes the earliest chapter from a singular start to a regulated passage. The next question is observational, because cosmology earns its credibility by confronting data. If a bounce happened, could it leave a trace in the sky we can measure? Or would it be forever hidden behind a curtain of thermalization? The early universe is a powerful eraser, yet it is also a careful archivist, preserving certain patterns with astonishing fidelity. The microwave background is both fog and fossil. A bounce can imprint features in the primordial power spectrum, which is the statistical fingerprint of early fluctuations. It can produce a cutoff at large scales, where the largest modes never had time to develop in the same way. It can produce oscillatory features, like ripples from a sharp transition, or altered phase correlations that differ from the simplest inflationary expectations. These are subtle signatures, but they are in principle observable. It can also affect primordial gravitational waves, the tensor fluctuations that stretch and squeeze space itself. Some bounces predict blue-tilted tensor spectra, meaning more power on smaller scales, unlike many slow-roll inflation expectations that often yield a nearly scale-invariant or slightly red spectrum. Detecting such a tilt would be a major clue, though it would require careful separation from astrophysical foregrounds. The signal is faint, and the universe is noisy. But predictions are model-dependent, and this is the recurring discipline of the chapter. The same flexibility that makes bounces possible can also make them hard to falsify, because parameters can be tuned to hide features. A responsible comparison asks which predictions are robust, not which can be engineered. The goal is not to win a contest of imagination, it is to narrow nature's options. So we separate three levels of claim, because clarity prevents overstatement. Level 1 is mathematical consistency, meaning singularity avoidance in a controlled approximation, with equations that remain well-defined. Level 2 is cosmological viability, meaning a smooth universe with the right perturbation statistics and a credible thermal history. Level 3 is testability, meaning distinctive signatures not easily mimicked by other mechanisms. That last level is the hardest, because the early universe is a place where different stories can converge on similar outcomes. Inflation, bounces, and other mechanisms can all generate nearly scale-invariant spectra under certain conditions. The discriminators often hide in non-Gaussianity, tensor spectra, or detailed scale-dependent features. The data are improving, but the theoretical space is wide. Now we turn to cyclic and ekpyrotic ideas, where contraction is not a bug but the main feature. These models often aim to replace inflation's early accelerated expansion, while keeping the virtues inflation is praised for. Historically, they gained attention in the early 2000s, partly as a response to concerns about inflation's initial conditions and the possibility of eternal inflation. They offered a different route to smoothness, one that runs through contraction rather than expansion. In ekpyrotic scenarios, the universe undergoes a slow, ultra-stiff contraction, and the phrase ultra-stiff has a precise meaning. The equation of state is very large, so pressure greatly exceeds energy density in a particular sense, and the energy density grows faster than anisotropy. This changes the stability story, because the dangerous shear terms can be dynamically suppressed. The contraction becomes a smoothing engine. That slow contraction can smooth and flatten the universe, and it can act as a dynamical attractor, like inflation but in reverse time direction. In an attractor, many different initial conditions converge toward the same behaviour, which is exactly what cosmologists want when they worry about fine-tuning. The universe forgets some of its messy beginnings, at least in certain variables. The price is that the mechanism must be embedded consistently in a full scenario. The story is often motivated by higher dimensional pictures, which provide an intuitive stage for the drama. Brain collision models imagine our hot Big Bang as a collision or interaction between higher dimensional objects, with our observable universe living on a brain-like slice. The collision releases energy, heating the universe and initiating the hot phase we recognize. The imagery is cinematic, but the math is the real constraint. The brain language is a metaphor for a deeper theory, not an established fact, and it is important to keep that boundary clear. The key point is that the hot phase is triggered by a transition, not a singular beginning, and that transition can be described in different effective ways. Whether the higher dimensional picture is literal or emergent, the ekpyrotic idea focuses on the smoothing power of contraction. The Big Bang becomes a reheating event after a long prelude. Ekpyrotic models face their own hard problems, and they are not spared the demands of precision cosmology. They must generate the observed nearly scale-invariant scalar perturbations with the correct phase and amplitude, because the microwave background is unforgiving. In many versions, a single-field ekpyrotic phase produces a spectrum that is not right, often too blue and with the wrong correlations. The simplest version fails a basic observational test. Multi-field mechanisms can fix this, but add complexity, because additional fields introduce additional modes and couplings. The conversion from entropy perturbations to curvature perturbations must occur cleanly, and it must not generate unwanted features. This is where model builders work hard, adjusting potentials and interactions to match the data. The reward is a viable alternative narrative, but the engineering is delicate. They also must address non-Gaussianity, because the statistics of fluctuations contain more information than the power spectrum alone. Some ekpyrotic mechanisms predict larger non-Gaussian signals than simple inflation, which becomes a potential discriminator. Non-Gaussianity is like a fingerprint of interactions in the early universe, and it can distinguish between different smoothing mechanisms. The challenge is that current constraints are strong, and future measurements must be even sharper. They must also handle the bounce itself, because smoothing contraction does not automatically provide a non-singular transition to expansion. The bounce can require exotic matter, modified gravity, or quantum effects, and each option carries constraints. A bounce must avoid instabilities like ghosts or gradient catastrophes in the effective theory. It must also connect to a hot radiation-dominated universe without leaving contradictions behind. So ekpyrosis often pairs with a bounce mechanism, classical or quantum, and the full scenario becomes a chain of phases. There is a pre-ekpyrotic setup, an ekpyrotic contraction, a bounce, and a reheating into the hot Big Bang. Each link has its own assumptions, and the chain is only as strong as its weakest part. The elegance is real, but so is the bookkeeping. Now we compare what these models aim to solve, because motivations shape what counts as success. Inflation explains horizon and flatness and seeds perturbations, but it raises initial condition and eternal inflation questions, especially when certain potentials lead to self-reproduction. Eternal inflation can imply a multiverse, and that implication changes the philosophy of prediction. For some physicists, that is a feature. For others, it is a warning. Cyclic and ekpyrotic models aim to avoid eternal inflation and the multiverse it suggests, and they also aim to make smoothing generic through contraction. They try to turn the specialness of initial conditions into a dynamical outcome, rather than a starting assumption. Yet they can inherit their own version of fine-tuning, because the required potentials, couplings, and bounce conditions can be narrow and delicate. The debate is not about imagination, it is about robustness. So the scientific posture is careful, and the documentary keeps its tone exploratory rather than evangelical. These are serious attempts to extend cosmology past the singularity, not settled replacements for inflation. The field is constrained by data, but it is also constrained by theoretical consistency, and both constraints are unforgiving. A beautiful story is not enough. Now we return to quantum cosmology in its most direct form, where the universe is treated as a quantum object with boundary conditions. Instead of evolving through a bounce, the universe can be described by a wave function over possible geometries and field configurations. This is not a small step, because it asks us to quantize not just matter in space, but space itself. The usual separation between stage and actors dissolves. This is where Hawking's no-boundary proposal re-enters the story, with historical weight and conceptual audacity. Developed in the early 1980s with James Hartle, it was an attempt to give a precise meaning to a universe without a classical beginning. The idea is not that the universe has a boundary in space, but that the past is rounded off, like a smooth cap rather than a sharp edge. The metaphor is geometric, not temporal. In that picture, the classical notion of a first moment is replaced, and the language of time begins becomes less literal. The geometry can smoothly connect to a regime where time behaves like a spatial direction, a move often described using Euclidean methods. The point is not that time is secretly space, but that the path integral can be dominated by configurations where the distinction blurs. The beginning becomes a region where our usual labels fail. The proposal uses a path integral over geometries as a conceptual tool, and the phrase "sum over histories" becomes more than a slogan. One sums over possible spacetime histories weighted by an action, and the weighting favours certain configurations over others. In ordinary quantum mechanics, path integrals sum over particle trajectories. Here, the objects being summed are entire universes. The ambition is enormous, and so are the technical challenges. The goal is to compute a wave function of the universe, a function that assigns amplitudes to different large-scale geometries and field configurations. From that wave function, one hopes to infer which kinds of universes are more probable, at least within the framework. No boundary is often described as the universe having no edge in the past, like a surface that closes smoothly, removing the need for a starting point. The common visual is a sphere-like cap, smooth and finite, but the disciplined version avoids slogans, because slogans can hide assumptions. The proposal is a boundary condition, not a mechanism that explains why the laws exist, and not a guarantee of uniqueness. It still assumes a gravitational action, quantum rules, and a measure over configurations, and those choices matter. The mystery is shifted into the choice of boundary condition and the underlying theory. Another quantum creation idea is tunneling from nothing, and here the word nothing is famously slippery. In this context, nothing often means no classical spacetime, not the absence of mathematical structure or physical law. A small closed universe can have a non-zero amplitude to appear, and the process is described as tunneling in configuration space, not motion through pre-existing time. The universe does not pop into time. Time is part of what is being described. Here the language is treacherous, and the documentary slows down to keep it honest. Tunneling is a metaphor for a calculation of amplitudes, and the calculation depends on a chosen framework, including how one defines the relevant boundary conditions. The payoff is conceptual clarity about beginnings, because a universe can have no classical past and still have a quantum description. Yet the price is interpretive ambiguity. Different proposals can give different probability assignments, and the meaning of probability without external time is subtle. In ordinary settings, probability is tied to repeated trials or ensembles, but the universe is not a laboratory system with many reruns. One can define probabilities as measures over configurations, but the interpretation remains contested. The mathematics can be clean while the meaning remains debated. This is the climax tension of the chapter, and it is not resolved by rhetoric. We can trade a singularity for a boundary condition, but we must admit what we have assumed. We can replace infinite density with no classical time, but we still need a framework that tells us how to compute amplitudes. The beginning becomes less like a spark and more like a rule. Now we pivot from origins to selection. If there are many possible universes or many possible histories, why do we observe this one, with these constants and these regularities? This question is not a distraction, because modern high-energy theory often suggests many metastable vacua, and cosmology provides mechanisms that could populate them. Selection becomes a bridge between fundamental theory and observed parameters. Inflation's eternal versions naturally suggest a multiverse. where different regions exit inflation at different times and in different ways. Different regions can realize different low-energy vacua, different symmetry breakings, and different constants, because fields can settle into different minima. The picture is often drawn as bubbles nucleating in an inflating background, each bubble a pocket universe with its own effective laws. It is a striking image, and it is also a technical claim. In such a landscape, vacuum energy values might vary, and the cosmological constant problem gains a new kind of answer. Instead of explaining a tiny value dynamically, one can argue that many values occur and we observe one compatible with structure. The explanation becomes statistical rather than mechanistic, and that shift is controversial. It changes what we mean by predict. Anthropic reasoning enters at this point, and it is controversial because it can feel like surrender. It says some parameters are observed because only certain ranges allow observers, and therefore our observations are conditioned on our existence. For vacuum energy, the argument is concrete and tied to astrophysics. Too large a positive value prevents galaxies from forming, because accelerated expansion tears matter apart before it can clump. Too negative a value can cause rapid recollapse, shortening the time available for stars and chemistry, so a small observed value could be a selection effect within a distribution, and the argument does not compute the value from first principles. It constrains what can be typical, given that observers require long-lived structures. The reasoning is conditional, not creative. Critics object that anthropic reasoning can weaken predictive power, because if many outcomes occur, the theory risks explaining anything after the fact. If every value exists somewhere, then why expect a specific one here, beyond the fact that we see it? Supporters respond that selection is sometimes unavoidable, because in a vast ensemble, conditional probabilities can be the only meaningful predictions. The disagreement is partly scientific and partly methodological. The debate is not settled within theoretical physics, and the documentary treats it as a live argument rather than a verdict. It is a disagreement about what counts as explanation and what counts as test, and those are not trivial words. Some physicists demand sharp predictions that could have been otherwise, while others accept statistical predictions as the best available given the framework. The tension mirrors earlier tensions about time and beginnings. Even within multiverse frameworks, testability is the key pressure, because science demands contact with observation. One looks for indirect signatures, like bubble collision imprints in the microwave background, or statistical predictions from measures over vacua. Yet bubble signatures are constrained and hard to distinguish from mundane anomalies. Statistical predictions depend on how one defines the ensemble, which is where the measure problem enters. But measures are ambiguous, and the ambiguity is not a minor technicality. In an infinite multiverse, counting outcomes requires a cutoff prescription, and different cutoffs can change the answer, sometimes dramatically. One measure can favour young universes, another can favour certain vacuum energies, and the predictions can shift. The multiverse can feel like a triumph and a trap. It extends inflation's logic while threatening to dissolve the sharpness of prediction, and that is why it remains contentious. The documentary lingers on the visual contrast, a sky filled with bubbles, and a scientist's notebook filled with question marks. If the ensemble is real, we need a principled way to do statistics on it. If we cannot, then the idea risks drifting beyond empirical reach. Now we return to the central question, because it has sharpened rather than faded. If the Big Bang is not a beginning, what is the origin event and what do we mean by origin? In bounce and cyclic pictures, the origin might be a transition rule rather than a first moment, a law-like bridge between phases. In no boundary pictures, the origin might be a boundary condition rather than an event, a constraint on allowed histories. In multiverse pictures, the origin might be a generative process with no unique start in our patch, because our observable region is only one outcome among many. Each answer changes the meaning of nothing, and each answer changes what counts as an explanation. Yet none of these proposals fully escapes the deepest demand, which is easy to state and hard to satisfy. They still assume a framework of laws, degrees of freedom, and quantum rules. So we keep the tone mysterious but disciplined, because discipline is what makes mystery productive. Physics can replace a singularity with structure, but it may not answer why there is structure at all. It can show that nothing in physics is really empty, but it cannot, at least not yet, justify the existence of the rules that make emptiness structured. The boundary between physics and metaphysics is not a wall, but it is a line we must mark. Now we bring the discussion back down to matter and energy, because origins are not only about geometry. Any successful early universe story must explain the contents, not just the expansion. The universe is not merely a metric. It is a zoo of particles, fields, and symmetries that behave differently at different temperatures. A pre-Big Bang scenario that changes the thermal history can change what survives into the present. We need baryogenesis, the process that produced more matter than antimatter, because the visible universe is made of matter with only trace antimatter. The conditions for baryogenesis are known in broad strokes, thanks to Sakharov's criteria from 1967. We need a mechanism that violates baryon number, violates C and CP symmetries, and departs from thermal equilibrium. Without those ingredients, matter and antimatter would annihilate into radiation, leaving a very different cosmos. Inflation can dilute any earlier asymmetry, so baryogenesis often must occur after reheating, when the universe is repopulated with particles. That links particle physics to the end of the earliest phase, and it makes the details of reheating more than a footnote. If the universe bounced, the analogous question becomes when and how the hot plasma was produced after the bounce. The narrative must connect to a concrete thermal bath. We also need a story for dark matter genesis, because dark matter shapes galaxies and large-scale structure. Thermal freeze-out, freeze-in, axion misalignment, and other mechanisms depend on the temperature history and the expansion rate. Change the pre-Big Bang story, and you can change the relic abundances, sometimes by orders of magnitude. A longer contraction, or a modified early expansion can shift which candidates remain viable. Different pre-Big Bang scenarios can also alter the timing of phase transitions, such as electroweak symmetry breaking or potential new transitions at higher energies. Those transitions can influence baryogenesis, gravitational wave backgrounds, and the distribution of relics. The documentary does not open a new chapter here, it stays with the same theme. The point is that origins must account for both geometry and inventory. We also face the hierarchy of parameters, and the question is as old as modern particle physics. Why do coupling constants, masses, and symmetry breakings take the values we measure, rather than nearby values that seem mathematically possible? Some approaches hope for dynamical selection, where the early universe drives parameters toward attractor values. Others accept environmental selection in a landscape, with anthropic constraints as part of the inference. The documentary does not claim closure here, because closure would be dishonest. It marks the edge where cosmology meets particle physics, and where explanation becomes layered, with some answers dynamical and others statistical. We can compute abundances given a scenario, but choosing the scenario remains the deeper task. The most honest stance is to show the structure of the problem. This is the narrative peak of the series' tension, and it is meant to feel unresolved in a precise way. We can model the early universe with increasing precision, yet the word origin keeps slipping, because it depends on what we mean by time, law, and boundary. If time emerges, there may be no before, only a deeper description in which before is not defined. If time extends, there may be a before that is hidden behind a bounce or a quantum boundary. Either way, the Big Bang becomes less like a first cause and more like a phase change, like water freezing or boiling under cosmic conditions. The beginning becomes a question about the rules of phases and about what happens when the variables we use, time, distance, curvature, stop behaving classically. The universe's earliest chapter may be written in a language we're still learning to read. That is not defeat. It is an invitation. Now we pivot toward what comes next in the series. The final chapter must synthesize what we can claim, what we can test, and what remains open, without pretending that open questions are flaws. We have learned that nothing in physics is rarely empty, because the vacuum is structured. Quantum gravity may regulate singularities, and boundary conditions can replace first moments. We have also learned that every replacement carries assumptions that must be named. Yet the deepest question survives in a refined form, and it is sharpened by everything we have seen. Why these laws, why this structure, and why this capacity for a universe at all? Physics can move the boundary of explanation, and it can make the boundary more precise, but it may not erase the boundary entirely. Chapter 7 will gather the threads and state the most honest answer, scientific and provisional, and still beautifully mysterious. We end where we began, with a word that keeps slipping under scrutiny and changing shape in the light. Nothing can mean empty space, with galaxies removed and only geometry left. an austere stage of distances, angles and curvature. In that picture, the camera drifts through darkness, and the darkness still has structure. It can mean the quantum vacuum, a lowest energy state where fields never truly sit still. Even at zero, quantum uncertainty jitters, brief fluctuations that borrow energy within strict limits, then dissolve back into the ground state. It can mean no classical spacetime at all, only a quantum gravitational state where space and time are not yet smooth. In that regime, the familiar grid of coordinates may be an approximation, like a coastline that looks continuous until you zoom in, or it can mean absolute philosophical nothing, with no laws, no possibilities, no mathematics, no rules for anything to happen. Physics can address the first three levels, at least in principle and partially in practice, because each still contains a describable framework. It cannot yet address absolute nothing, because explanation already assumes a language of relations and regularities. That is why definitions matter, and why slogans mislead more than they clarify, especially when a single word is asked to carry 4 different meanings. Now we answer the central question cautiously, without pretending the mystery is solved. Modern cosmology allows plausible mechanisms where a universe emerges without a classical cause, meaning without a prior event inside ordinary time. Quantum fluctuations, vacuum-like energy, and inflation-like dynamics can amplify a tiny patch into a vast smooth cosmos. Inflation, if it occurred, would stretch microscopic irregularities into macroscopic patterns, leaving faint statistical fingerprints in the sky. Yet this is not creation from strict nothing, because the laws and quantum structure remain. The nothing here is already a physical state, defined, constrained, and mathematically articulated. Now we reconcile Big Bang language with the idea of beginning, because words like origin can smuggle in the wrong picture. The Big Bang marks the start of our observable hot phase, not an explosion into pre-existing space. Visually, the scene is not a fireball expanding into darkness, but space itself swelling everywhere at once. The singularity is best read as a sign of incomplete classical theory, a warning light on the dashboard of general relativity. Historically, this shift took time. Einstein's equations allowed expansion, and observations later forced the issue. Origins likely require quantum cosmology, where time and causality may be emergent rather than fundamental. Now we evaluate universe from nothing claims with the same discipline, because the persuasive power often hides in the chosen definition. Krauss-style framing explains how a quantum vacuum can produce particles and even spacetime-like behavior. It assumes fields, a ground state, and stable laws that define probabilities, including the very notion of what counts as allowed. The argument is powerful within that definition and incomplete outside it, because the deepest question becomes why that framework exists at all. Now we ask what would count as evidence, because origins must meet observation rather than rhetoric. Primordial gravitational waves would be decisive, especially through improved CMB polarization and B-mode searches. Those patterns would be a delicate swirl in ancient light, an imprint of ripples in spacetime itself. Better CMB maps and large-scale structure surveys can constrain inflation potentials and non-Gaussianity, tightening the range of viable early universe dynamics. Signatures of bounces or non-inflationary initial conditions could appear as large-scale anomalies or distinctive tensor spectra, subtle features that refuse to average away. Near the Planck epoch, models proliferate because the data thin and the mathematics is hard, and because quantum gravity is not yet a settled theory. At energies where spacetime may be granular, different formalisms can mimic each other's predictions. Physicists weigh internal consistency, elegance and testability, then wait for nature to choose. For now, honest limits are part of the story, not an embarrassment, because precision about ignorance is how science keeps its footing. We can end the search for a simple nothing without ending the mystery of existence. Our best theories turn nothing into a structured quantum question, not an empty void. The deepest puzzle may be why there is lawful structure at all, rather than chaos or silence. Spacetime, quantum fields, and mathematics seem capable of birthing universes, and we still do not know why. In that remaining gap between what physics can model and what philosophy demands, the frontier stays open, and the darkness stays meaningful. We began by separating ordinary emptiness from cosmology's stricter nothing, and by treating the Big Bang as evidence for a hot, dense history, not a proven first moment. Redshifts, the CMB's black body glow and ripples, and the light element chemical receipt let us rewind with confidence until the trail reaches the Planck epoch where our equations stop agreeing. There, spacetime itself becomes the suspect, and the mystery shifts from what exploded to what counts as a beginning, when time may be emergent and geometry may be quantum. Along the way, physics taught us that the vacuum is not blank. It is structured, measurable, and restless under constraints like the uncertainty principle. Inflation then offered a bridge from microscopic jitter to cosmic architecture, stretching quantum fluctuations into the seeds of galaxies, while leaving behind a set of fingerprints we can still hunt in precision maps. Yet inflation also raised sharper questions about what ignites it, whether it becomes eternal, and whether a multiverse can be made scientific without losing the meaning of probability. And beyond inflation, bounces, cyclic models, and no boundary or tunneling proposals tried to replace the singularity with a boundary condition, a transition, or a rounding off of time itself, each compelling, each haunted by testability. All those threads converge on a single lesson. The word nothing is doing too much work. Sometimes it means empty space, sometimes the quantum vacuum, sometimes no classical spacetime at all, and sometimes the philosophical absolute. No laws, no possibilities, no mathematics to even state a question. Modern cosmology can speak to the first three because they still have structure to calculate with, but it cannot fully speak to the last, because explanation assumes a framework in which explanations can exist. Even the vacuum energy story, so central to inflation and to today's dark energy, reminds us how unfinished the picture is, because quantum field theory and gravity still disagree by an almost unimaginable amount. So the finale of our journey is not a single model crowned victorious, but a clearer map of where evidence is strong, where language misleads, and where the next decisive measurements must aim. We now know what the Big Bang most reliably means, the beginning of the observable hot phase, not necessarily the birth of all reality. We know why the singularity is best read as a warning light, not a literal point of infinite density, because it marks the border where classical spacetime stops being a trustworthy stage. We know the early universe left records in acoustic peaks, spectral tilt, near Gaussianity, and element abundances, and that future records may hide in B-mode polarization, tensor spectra, subtle non-Gaussian patterns, or large-scale anomalies. And we know that competing origin stories can imitate each other's predictions, which is why the central discipline of this field is not certainty, but precision about ignorance, paired with a stubborn demand for observational hooks. What replaces classical coordinates at the Planck boundary is still unknown, whether it is quantum foam, discretized geometry, or spacetime emerging from deeper correlations. The problem of time remains a clue as much as a headache, because if the universe has no external clock, then before becomes a relationship, not a location on a timeline. The cosmological constant problem still stands like a riddle carved into the foundations, asking what principle makes vacuum energy small, and why it can drive expansion without overwhelming everything. And the hardest question remains untouched by any equation, why there is a lawful arena at all rather than the philosophical nothing that cannot even host a law. But if this sounds like defeat, it is the opposite, because the boundary of knowledge is exactly where physics becomes most honest. We have learned to speak carefully about origins, to distinguish a thermal beginning from an absolute beginning, and to treat from nothing as a claim that must declare which nothing it means. We have learned that the universe can look like it was born from a whisper, because quantum fluctuations, once amplified, can become the scaffolding of stars and minds. And we have learned that the same tools that reveal our limits, CMB maps, primordial chemistry, and the mathematics of quantum gravity, also point to the next experiments that could force our theories to choose. In other words, the story so far is not nothing became something, but the simplest state allowed by the rules may already be fertile. If space-time can emerge, then the origin question becomes less about a first event in time, and more about the conditions under which time itself becomes meaningful. If the vacuum is physical, then empty is not the absence of reality, but a particular kind of reality with constraints, symmetries, and energy that can shape the cosmos. And if multiple scenarios survive today, it is because nature is subtle, and because our best data still comes from a universe that had already cooled enough to let light travel freely. That is why the conclusion we can honestly offer is both scientific and provisional, and still genuinely mysterious. The universe may not have begun from nothing in the philosophical sense, but it may have begun without a classical cause, from a quantum state where the line between absence and existence is not sharp. The Big Bang may be the start of our observable chapter, while the deeper book begins in a regime where before is a misused word. What we call nothing in modern physics is rarely empty, and that may be the most unsettling and most beautiful answer we have. Call back to the opening question. Before the first tick of time, there may not have been a where for nothing to exist, because where and when could be late arrivals. When physicists say nothing, they often mean a lowest energy quantum state or a no classical space-time boundary, not the absolute void of philosophy. And that difference is the whole story. Final thought. If the universe can rise from a state that still contains laws, fluctuations, and possibility, then the real mystery is not how something defeats nothing, but why possibility exists at all. And perhaps the most profound idea is this. The beginning may not be a moment we can point to, but a transition in how reality keeps time. Call to action. Watch the next generation of measurements, B-modes, non-Gaussianity, and large-scale surveys, because the sky is still writing clues about what nothing really was. Before the first tick of time, there may not have been a where for nothing to exist, because where and when could be late arrivals. When physicists say nothing, they often mean a lowest energy quantum state or a no classical space-time boundary, not the absolute void of philosophy. And that difference is the whole story. If the universe can rise from a state that still contains laws, fluctuations, and possibility, then the real mystery is not how something defeats nothing, but why possibility exists at all. Perhaps the deepest answer is also the strangest. The beginning may not be a moment in time, but the moment time becomes real. Watch the next generation of measurements, B-modes, non-Gaussianity, and large-scale surveys, because the sky is still writing clues about what nothing really was.